Fantastic. Well, welcome everybody to the first SSG Connectomics virtual course. I want to thank all of you for joining. Looking through the course list before, I know we've got members joining from around the world. So good morning, good afternoon, good evening, whatever it may be, wherever you are. But thank you for joining us. We've got a course lined up today that I hope you will find valuable. I want first to thank Monica and the team at the SSG for all the work that they've done to put this together. And particularly I want to thank Dr. Michael Sughrue for joining us. For those of you who know Michael, he is a great leader in neurosurgery and a dear friend of mine. He grew up in a small town in Oklahoma and then went to New York City to attend Columbia University. From there, he traveled west to UCSF, where he completed his residency. He joined the faculty at the University of Oklahoma after that and served as director of the Brain Tumor Center. He was there for 7 years and was remarkable and remarkably accomplished as an academician and a surgeon during that time. During this time, he developed a great interest in Connectomics and the white matter anatomy of the brain. As you can see in the output that he's really led this field over the last decade. Since that time, he's authored over 250 scientific publications and 4 textbooks. He, until COVID decided otherwise, somehow managed to balance being a remarkably busy surgeon with being a remarkably busy world traveler. He's moved to Sydney. He's been there since 2018. And while in Sydney, he has now founded Omniscient Neurotechnology, which is an AI startup company that's aimed at radically accelerating the evolution of our understanding of human brain disease and mental illness and bringing these technologies into the clinic. And it's this idea of translating that I've always been impressed with Michael, even from the time that we met before when I was a resident and he was just looking to see where he was going to train. He's always been critically engaged by this idea of knowledge being important for moving our field forward. I also want to introduce Brad Fernot, who is the Vice President of Omniscient Neurotechnology for North America. With that, I will turn it over to Brad and Michael.
Thank you. Hi, everybody. This is Brad Fernald, VP for the US for OmniNeuro. And I want to address a few housekeeping issues before we get started related to the software you're going to be using. So today you'll be using a Connectomics software during the 3rd session of the course. And this software is an educational and research software focusing on connectomics. It is not currently cleared for clinical use by the FDA. You should have received instructions via email on how to register for the software and access the software with your browser. And we recommend that you preload the software and do not wait until the lab session. And that's because we won't be able to help everybody troubleshoot at that time if there's issues. So our suggestion is that you open the software during session 2 and leave it open. You can open it now as well, but it'll time out and you'll have to reload it. That's okay, it's easy to do, but if you wait until session 2 and load it, you should be good. If you have the opportunity to use 2 screens, one for the Zoom and one for the Connectomics software, then this is highly recommended. And that's so that you can follow along with Dr. Sughrue, who's going to be leading you through scientific content using the software and also use your software at the same time. If you're unable to do that, for example, I'm using my laptop and I'll just put the Zoom meeting side by side with the software and that should work. There is a chat window in this Zoom conference. And if you have issues logging into the software, there's a link that you can click, which will launch a Hangouts, Google Hangouts with the technical team. And technical support team will help you resolve any issues logging in. There's the link now. Thank you, Leo. at the end of the course, there's an evaluation survey, and also note that for the CME credits to be awarded, you have to you have to have registered and complete the questions sent by the CME outfitters at the end of the meeting. The recordings of the course will be made available after the course. However, access to the software will cease. So, we won't be going into a lot of detail on the features of the software and how it works, technical aspects or applications. So if you either get behind and need more time with the software, or you want to explore more further what the software can be used for, then hang around afterwards and there'll be representatives from OmniNeuro that'll stick around and address those for you. And I think with that, I'll hand it back over to Dr. Doss or Mike Sughrue.
I guess we'll get into it because we've got a lot to cover. So let me make sure that I'm still screen sharing here. Yeah, somehow I stopped doing that. Okay. Okay, so thanks everyone for coming. This is a kind of a unique first-in-class type of endeavor. And one of the benefits of being a software company, particularly a company that works in the cloud, is that we have the ability to teach how to utilize this technology a lot faster. And so this actually, interestingly, COVID-19 works very okay in our business model, and it works well with our software. So we came up with the idea of how can we teach a lot of people about Connectomics, how to use it, and really to take it beyond just me talking about anatomy or my research or whatever. So I'm going to start with a disclosure. Obviously, I founded the company. I tell everyone that I founded a startup company to fund my research habit. And as Brad pointed out, while we're in the process of taking this through the FDA, this has not been evaluated yet. We hope that one day that it will be in the near future. But for right now, what you're looking at is just something on the frontier of science. So how we're going to cover this is the first thing I'm going to do is kind of give a course that I've given about 40 times now in some form. And what we're really focusing on is how do we improve people's understanding about how the brain works, to how do we utilize Connectomics in the real world. And that again, any of these topics by themselves could be their own full day course. So we're a little bit pressed for time, just because we're trying to keep this into something that everyone can attend. And then we're going to start actually using the software. And part of it is it's all great and well to talk about, hey, great, Connectomics can tell us some interesting things. But if we can't do it in the real world, it's not going to actually help patients. So we're going to start working towards showing everyone how to actually utilize this in surgical planning. And at the end, we're going to cover a new concept that we've been working on in Sydney for a couple of years now, that we call interventional neurorehabilitation. And we'll talk about what that means here in a second. And we'll go through at least my first iteration on how to pick targets for doing this kind of treatment. So Connectomics, what is it? For those of you who've never heard me give this talk, omics is just a generic term for big data, and Connectomics was, and the connectome was a term coined by someone named Olaf Sporns at the University of Indiana to talk about how to use big data techniques and machine learning and graph theory and other things to make sense of the massive complexity of the brain. Now, there's a lot of different ways. Connectomics can even be down to the level of track tracing, microscopic connectomics, but that's not really what we mean when I'm giving this lecture. We're really talking about macro and at most mesoscale connectomics, and this means it's mostly MRI based because when you get into the depth of fMRI and tractography, these data sets are far richer than we've given them credit for, and it really utilizing powerful software and doing things on the post-processing has a really important role in making these imaging make sense. So as far as the majority of people who signed up for this course, Connectomics really comes down to how do we look at a disease like this? And instead of just looking at the tumor, understand what the network and brain anatomy surrounding it is, work this into some kind of actionable plan that leads to a better mixture of risk and benefit for the patient. So for surgery, that we kind of all are familiar with the concept. And it's important to note that absolutely none of the core technologies that we're talking about are new. This goes back over 30 years. There's 550,000 papers, and the methods are well described. This is not controversial topics here. But the question is, why do we not get this? And there's a lot of reasons. The biggest one we found, and I found at the University of Oklahoma, where I didn't have the Martino Center like at MGH, I didn't have a bunch of experts willing to help me with this, and this forced me to really address some topics at a really fundamental level that taught me a lot of lessons. And so ultimately what you find out is the software is freeware, and you get what you pay for. It requires you to code it yourself. It doesn't necessarily work interchangeably. It's not very fast. And so getting this done requires experts. And oftentimes having someone go down into the scanner and set up a task for a test-based fMRI. And when you get all this, you get a small amount of information and it's not clear what to do with it. And so it's nice to have pretty pictures, but ultimately we could be doing a lot more with this. And as I became more familiar with the area, I was really stunned at what people were doing with Connectomics that was very, very far ahead of what we were actually getting in the real world. And so if you basically don't spend some time trying to dig into the forest and figure out what's important and what's not, you get this, a really pretty desktop picture, but it doesn't really necessarily tell us what we want to know. So if you're an expert at this, you might think, well, that seems like a good site for language or something, but which part is language? And where's everything else? Where's cognition in here? And so then we have a limited number of actions. It's important to also note that when you look at an fMRI, this is what the derivative image looks like. It's kind of this grainy image done 168 times through all the whatever slices you have, 30 or whatever. But inside of this is a rich, rich data set. And most of this, if you're not looking into this, is getting thrown away or it's hard to analyze. So for example, if I were to take the bold signal at a point, this is what it looks like. Now, some of that's noise, some of that's signal, but more importantly, this is a combination of signals from multiple other parts of the brain. So staring at this is not that informative. Looking at this doesn't tell you what needs to happen, but inside of there is a lot of information that's actually useful and actionable. And the first step, and this is a step that we're going to go back to a lot, is inside of machine learning, one of the critical first steps is called dimensionality reduction, because ultimately even the best machine learning tools struggle when you're giving them a million data points. You have to start figuring out, what am I going to focus on, what am I not going to focus on? And perhaps the most familiar and powerful tool for doing that is parcellation. So what does that mean exactly? Well, parcellation is a way of breaking up the cortex into components that are similar in some way. So everyone here knows at least one parcellation scheme, which is Brodmann's parcellation. The Brodmann areas are a parcellation. That was what he was attempting to do. He utilized looking at stains of the neocortex. But there are other ways to parcellate, and there's been lots of parcellations over a while. This is actually my brain taken through and registered with the human connectome parcellation, or also known as the Glasser parcellation. And it's important because when you start tackling high dimensional fMRI data, particularly resting state fMRI data, what you find is that you have to be able to put some order into this. There's too many voxels and too many comparisons for this to give you meaningful results. And by taking areas and clustering them by similarity, you can reduce this from a several 100,000 dimensional problem to, in this case, 180 areas per hemisphere problem. And that's tractable. It's difficult, but it's tractable. So one way to look at fMRI in this way is I take the bold signal from two areas and I compare them in some statistical way, and I figure out how much they correlate. This is very simple to do, and there are more sophisticated methodologies, but they're all variations on this theme. And why do we care about that? Like, why is it important to know that two areas are firing together? This is a term called functional connectivity. There's also structural connectivity, meaning that there's a track between the two areas. But functional connectivity has been studied extensively. And basically, why we care about this is that areas that are doing a common function often fire together. Things that fire together often wire together. So most networks actually have a physical connection also. And we also know that abnormal functional connectivity is at the center of a lot of diseases. Whether it's causative or an effect or a manifestation of disease is a whole different question. But we know that most mental illnesses, in fact, most of them that have been studied, have abnormal patterns of functional connectivity. And this is non-trivial. So this is a paper in Nature Medicine where they took a series of depression patients and a series of anxiety patients. And the first thing they found is that they're basically the same patient population when it comes to functional connectivity, the same patterns emerge. So basically, they're variations on the same disease. The second is there is no such thing as either one of them. There are actually 4 versions of this disease, and they respond differently to treatment. So for example, if you were a biotype 1, meaning you had the functional connectivity pattern of biotype 1, then you had a much higher response rate to standard TMS treatment, which is right there, than if you were biotype 4. I mean, we're talking, 5 or 6-fold difference. And so what this means is that functional connectivity has the potential to predict and guide treatment, even in diseases that do not have obvious structural correlates. Now, it's important to note that when you talk about big data, you're talking about machine learning. And this often gets conflated with AI. In fact, our chief data scientist often jokes that if it's written in Python, it's machine learning. If it's written in PowerPoint, it's AI. But we kind of don't think of ourselves that way. And one of the things we pointed to is there's a whole other concept called IA, which is intelligence augmentation. So what's the difference? And why do we think that IA actually has a much bigger bandwidth than AI? Well, AI, these kind of things. This is things like facial recognition. And there's a number of people working in this area. And what they often are trying to do is get a machine to recognize something at a rate similar to a radiologist, for example. And this assumes that the radiologist is doing a reasonably good job. And in some cases, they probably are. They're probably pretty good at picking up pneumothoraxes or hydrocephalus or things like this. But I think anyone who's had a serious thought of been a neurological doctor for any period of time knows that there's a lot of things we're not good at. Diagnosing functional disease, knowing what's actually happening in the brain that doesn't have an obvious structural explanation. And in this situation where machine learning it can be used intelligently, is to make things visible that are otherwise invisible. And it assumes that we're bad at the task. Again, if we were good at looking at bold signal and cross-correlating it, we wouldn't need machine learning to do that. So AI is an optimization. IA is an improvement. So going back to this parcellation, this came out in Nature in 2016, and it's by the Human Connectome Project. And again, I could spend an hour on this slide if we really wanted me to. It's a very complicated slide. But basically what they did was, in short, a large number of very high quality fMRIs of almost every conceivable type, task, resting state of all kinds, myelin maps, you name it. And then they spent several years figuring out the boundaries that were consistent across individuals that were unique. So when they said that this parcellation was different than this is because on some tests, they behaved differently. And what they estimated is there's about 180 unique areas. And what's surprising is, in most cases, these are reasonably consistent between people. So there's only a certain number of ways the brain can align. So while there's individual variability, it's not extreme. And it's almost the week this came out, I immediately gathered together a bunch of students and some residents, and we basically started mapping this in a lot of detail. I first just wanted to know for my own purposes, but then eventually, luckily, when this got really out of hand, we managed to be able to put this into a supplement in neurosurgery. And what we were trying to do here was to figure out where everything went. Let's just get a very simple who's who in the zoo of the functional connectivity, which you see here, and the structural connectivity. But again, having a wiring diagram is interesting, but white matter is a means to an end. Okay, so we do it because we want to ultimately say function. And a lot has been studied in the fMRI literature. In fact, it's massive. And we didn't want to necessarily throw all that out just because we have a new scheme. What we wanted to do was use a technique called coordinate meta-analysis, where we take fMRI coordinates from the literature, this here is language, map them onto parcellations. So what you see is this is incorporating the world's literature on where language is activated in the human brain. And so we can figure out who those areas are, and then make them into network maps. So yes, we don't know all of the connectome, but we have some things that we have a pretty good idea what they're doing. And this, as you can see, of our language system is not totally radically different, but it's a little bit more sophisticated. There's areas that don't show up in the traditional language, and we'll talk about that in a little bit. But again, there's a big challenge. One of the challenges is it's all great and well if we have an idea about how the brain works. That always improves it. But if we don't get this information on individual patients and can customize it, it's only so actionable. It's just something we lecture to our residents over our shoulder and hope that they incorporate that into their worldview. Now, how do you take a brain and figure out where things are? Well, this is a problem called atlasing. So what do I mean by that? Atlasing is when I take a set of parcellations from a generic average brain, averaged over many, many people, and I warp it to fit the brain that I'm actually looking at. And doing this just with standard coordinate schemes does okay in normal brains. I mean, it misses a spot here, it misses some spots here, it's a little bit of misalignment here, but it's not bad, right? This isn't something that we would say is way off. But this is the kind of patient that I saw, and I realized that in order for us to really translate this, we first had to be able to get a situation where we could handle anything that you put into the scanner. And this is a machine learning problem. And luckily, I managed to meet up with people who could solve this problem, who were interested in helping me tackle this. And what we came up with was a technique called reparcellation. And so what reparcellation is we taught a machine learning model about how every part of the brain talked to every other part of the brain. Now, this is based on tractography. Specifically, it's the next generation of DTI called constrained spherical deconvolution, or CSD. CSD shows crossing fibers better, so we think it has some stronger arguments for utilization of mapping the brain, and also it's a clinically achievable parameter. And what we did was we taught the machine what the connectivity pattern of every voxel, what does a voxel of Broca's area do? Who does it talk to? And once the machine knew how to do that, we could basically take a situation where things had been moved around by a tumor and recluster them, saying, you're actually in the wrong spot compared to what this atlas says, we reassign you. What that means is the shape is irrelevant. So to give an example of what I mean by that, this is the absolute worst DTI I could possibly find in my set of several hundred that I've run through this by now. I spent several months blasting scans through the algorithm. This is the worst one I could find. So it's had a previous large frontal lobe resection, non-operative recurrent glioblastoma, but even then the machine learning model could find the caudate and putamen. And that's really interesting because the insula is shifted into the space that was removed. The machine learning can also tell us when areas are missing or when areas have moved. And when you apply a Demon correction algorithm like we have in the CSD software, it's able to give you really interesting maps, because even though the tumor has distorted the SMA, it still can find very plausible locations for the SMA and very plausible connectivity patterns running through the tumor. Now, what we don't know, and this is a scientific question, is are these doing the same thing in this patient that they do in normal people? We don't know. It may be that they've taken a different role on, or they're irrelevant. We don't know if these fibers are important. That's a scientific question. What we do know is that they're plausible. And this has significant ramifications, particularly for glioma surgery, because whether you admit it or not, you are not inside the tumor completely. Either that or you're leaving a lot of tumor. So you're doing something that is, you got to bend somewhere. And so what we're really doing when we do safe and effective brain surgery is making a decision based on our understanding of the situation that balances those two competing goals. This has been pointed out by a lot of people. And ultimately, what the role of this kind of imaging is not to necessarily protect you from doing anything stupid. It's to help you make better decisions in the operating room based on data. And the better we understand this, the better decisions we make. So here's a simple way to apply this. So again, if you look at this large frontal tumor, and we'll go into this a little bit about a medial frontal disconnection. But basically, in this situation, our machine learning can demonstrate that there are 3 networks that are at risk. Obviously, anyone who's experienced with this knows that this is going to be abutting at least the beginning of the motor cortex in the posterior region, and as well the default mode network and the central executive network, which we'll talk about in a later lecture. And so ultimately, this allows us to come in with a mental picture that these are the 3 divisions that we're fundamentally doing, and here's where the risk lies. So while you can't guarantee there's millimetric accuracy with tractography, there isn't. We know brain shift causes this. What it does is it frames your thinking, and so you have an idea of what you're there to do, because of course anybody who's being rational and thoughtful about gliomas knows that you can't see all these structures when you're cutting them. Another possible application of this, and we'll talk about, is interventional neurorehabilitation. So what does that mean? That's a term that I coined to describe what we were trying to do for patients with gliomas, to try to drive reorganization of the connectome for therapeutic gain. I'm not sure how grain got in there. But the thought is that how do we utilize insights from Connectomics to make decisions and provide safe and effective therapies that improve our patients' chances of getting better? And there are a lot of potential options. I'm sure many people on this call who are fairly creative individuals can come up with ideas, but the most available one right now is transcranial magnetic stimulation. It's an FDA-approved treatment. We've been using it off-label in Oklahoma, and also a lot in Sydney now. And what this does is this stimulates the brain with a magnet through the head. So let's say you take this generic atlas, you utilize machine learning to adjust it. So now this is personalized to the patient. You can then take that parcellation and use it to dice up and analyze all the correlations between every area and every other area, meaning every parcellation with everybody else, including basal ganglia, as well as the tractography. And you get these matrices. These matrices show you how every area talks to every other area. You can then turn machine learning on and say, well, what's abnormal here? And now you have an idea of what you can act on. So again, as we look at the functional connectome, we're looking for areas that are supposed to fire together that are not firing together, or the converse, areas that are firing together too much, more than they're supposed to, both of which can be pathologic. And when you do this for the entire connectome, you get a matrix that looks like this. And this is, I calculated this out last night to get the exact number, but it's 143,600 comparisons. And what that means is this is all the parcellations in both hemispheres and the basal ganglia and all the other ones. And when you get a red square, these are areas that are talking together a lot. Doesn't mean too much, just a lot. And these are areas that are opposite each other. They're anti-correlated. But one of the things about it when you link it to a parcellation scheme that you know a lot about is that we know who everyone is, or at least we have a lot of areas that we know. There's a few that we don't. And furthermore, this causes, because networks fire together, these squares that go down the diagonal, because this is sensory motor areas with sensory motor areas. Again, this is an ordered matrix. And so that's why you see this. It's not random. I've structured this intentionally to show this. But again, when you look at data sets this big, human beings are, it's not new to show correlation matrix. They're all over the medical literature. One of the challenges, though, is that without knowing where to look and what to look at, then it's only so useful. So what we built in the background in the cloud is a large-scale industrial-grade machine learning workbench. So what this means is you can basically take 1 million of these with a clinical question and start directing it towards which one of these squares actually starts to predict outcomes, starts to cluster with symptom complexes, et cetera, to try to basically make this useful. Now, as we began to accumulate this, you can subset the matrix and provide useful information. So this is a patient with a glioblastoma in the language system. This is what a normal language network looks like. Again, the language areas versus themselves. So mostly red squares here. And this is what that patient looks like, a lot of blue. Part of this is these areas aren't talking to each other anymore. It's actually in the arc of fasciculus. And this is not surprising. What's interesting is that we can actually see it. And more importantly, that there's an area right there that exists in the real world, and we can actually pick areas, columns, parcellations, and direct the therapy towards this. So what you're doing is you're basically looking at the connectome, deciding what you want to change, and then doing something to try to improve function. And we've been doing this for a while, and while some patients don't see benefit from this, most do. And sometimes this is very, very obvious that this is not just spontaneous recovery. And so, again, machine learning takes this very, very large data set and could show us what's not normal on it. And what this does is, even though this is very high dimensional data, we can chop this down into something that's understandable with appropriate visualization and subsetting tools and machine learning to augment people's intelligence. So what is this anomaly detector matrix? And we're going to go over this in a later part of the course. What is it actually showing you? Well, in white, these are areas that trained on a cohort of normal, or at least healthy individuals. This is within the range of areas of how these two areas talk to each other. So if you see a white square there, that says that this area and this area talk roughly normally to each other. Black areas or red, blue areas are areas that are less than normal. Red are over-correlated, meaning these two areas are too correlated with each other. And these black areas we actually black out. And the reason we do that is that when you're looking at a number of comparisons, you're going to run into a statistical problem called the false multiple comparisons problem, and you're going to get a false positive rate. So what we did is we just took the most areas that fluctuate way too much in normal people, and we blacked them out. We don't want you to go after stuff that's very likely to be noise. Now, looking to the future, what else can we do with this? And these are things that, in some cases, we have the technology, but we haven't built the visualization tool. This is something we're still working on. In some cases, these are things that are looking to the future. And how do we make a weapon that allows us to go in to a surgery and have a much better idea ahead of time what are going to be the consequences of that surgery? Right now, we guess. And we assume redundancy, and we know that in some people that's true, and some people it's not. Well, one possibility that we've explored and published on is what's called graph theory. And so graph theory is a mathematical field of mathematics that has been applied to a brain analysis on multiple levels. It has a very useful way to take a highly complex network and to test hypotheses on it. So what you do when you make a graph is you take either the functional connectivity or the structural connectivity data between every point and every other point, and you represent them as lines on the graph. Now, that doesn't seem, it looks like a cool picture, but what the truth is that through mathematics, we know that certain properties tell us certain things about how things are connected. And this allows us to run experiments on brain data. So one experiment that we ran, it's a very simple one, which is you say, who are the centers of the graph? How does information flow in the graph? And you can measure this a couple ways. So one is what's called degree centrality. It's very simple. The degree of this node is determined by these three guys. So this was a parcellation. This parcellation would theoretically have a degree of 3 because 3 guys talk to it. But again, he's probably less important than this guy who talks to another equally important guy. And both of them are less than this guy who talks to 2 equally important guys, but all of them would have a degree of 3. So this last one called PageRank centrality may strike you as it sounds like an internet term. And the reality is this was Google's original search algorithm. That's what the original IP of Google was, using PageRank centrality to rank internet websites. But again, it's just a theory from graph theory. And so we looked at a variety of these guys, and we looked at PageRank centrality. We published it in the Journal of Neurooncology last year. And what we did was we said, okay, these graph theory things are interesting, but do they tell us something useful? So we went in and we said, let's take a group of individuals and ask, who are the highest centrality nodes? Who's the highest page rank? And luckily, because we know who's on this list, we knew that these guys here are in the Spetzler-Martin scale's eloquent areas. They're primary visual, motor planning, Broca's area, areas that are important. And actually, if you look at the other guys on this list, I can make arguments that they're also important. So these are the guys who are the highest centrality areas. So what we've been talking about is when we call something eloquent, we're meaning that it's a hub. And we also know that hubness in Alzheimer's disease is where the disease focuses in a lot of cases. So the question is, if hubs are eloquent, if we're calling it what we mean are the same thing, should we avoid hubs even if we don't know what they do? Again, that's a clinical question, but we now have the ability to study this. Next question, is this the reason why some patients get through a brain surgery and do fine, and other ones having the same or even smaller surgeries are hurt because we're missing hubs that we don't know about? Again, these are important questions that we need to answer, and now it is answerable. Here's another one. So we took, in this case, the parcellation, these are all the parcellations, and what we did was we ranked parcellations based on centrality, or regions. So this, you can't read this, but at the very top, that's the brainstem. So in everybody, it's the hub of the brain, right? Nothing surprising. We know that the brainstem is a hub. And if you look here, these are a lot of basal ganglia areas, but you get below there, you have a fairly consistent list of areas that have the highest centrality, okay? So if you're concordant with your area, if you're up here, you should be green. And if you're down here, you should be red. However, there are some circumstances where you see there's a parcellation that differs between individuals, occasionally. So this is a trap, right? This is actually even worse trap, because in this individual, we think that it's fine, but turns out, actually, no, that's a hub. And so what this tells you is that this is probably a lot of what we've seen of people who don't do as well as we expect. We're not really taking into account how their network is really working. Another question is, how do we save cognition? And this is actually why I got so enthusiastic about Connectomics many years ago. I wanted to know how not to have patients come back in my office and tell me I can't go back to work, and I don't have an answer other than, well, you don't have hydro. And so we started digging into how does the brain do this in the first place? And what is the cognitive part of the brain? And looking back on when I first started asking that question, it's a stupid question, right? I didn't know better. What we now know from a lot of very good studies covering multiple types of evidence is that higher cognitive abilities don't result from a place in the brain. They result from multiple networks working together in some combination for some period of time to make magic happen. I think about this as like an orchestra, and we'll talk about this. And how networks communicate is really important. And one of the ways, that people have dug into this is a concept called path length. You can measure path length. How far does it take to jump across the brain graph? How many steps? And why we care about this is there's studies that show that the shorter your average path in your brain is, the smarter you are. It correlates with IQ. So what do I mean by path length? So let's say this is the brain graph. Each one of these is a parcellation, and the number is how many tracks go between A and B. And so let's say I want to measure the path length between A and B. Well, I just showed you the shortest path, okay? And again, there are other paths, but they have fewer fibers, so that we would assume that the signal transduction is probably not, again, probably when a signal goes from A to B, it doesn't travel on this path. It travels on all possible paths. This is just the one that matters because of how connected it is and how short it is. But then when we're talking about surgery, we do that. We delete parts of graphs. That's what neurosurgeons do. So the question is, what happens when we force the brain to go down a different path? Is it relevant or not? And so in order to do that, what we did was we took tractography, we parcellated it, and then we made an algorithm to calculate every possible path in the brain and measure what's called global efficiency. This is kind of 1 over path length. So if you're efficient, you have short paths. And then what we did was we did another algorithm, and we said, do every possible surgery you can do. Not every possible, anything that you could come up with, plausible surgery. So what this means is these are allowed, they're continuous, but you don't have parcellations on opposite sides of the brain, because very rarely do we do anything like that. So we basically came up with an algorithm that generated all the plausible brain surgeries we could do, and then we did that to the graph. And then we calculated efficiency. And what we're trying to do is say, what's the impact of an operation? So If everything is eloquent, okay, then we can't do brain surgery. So what we're actually talking about is, how do we study what is not tolerated? Everything is doing something. It's not there to collect CSF. It's there to do something. And so if shorter paths mean higher IQ, it's reasonable to posit that increasing the path length significantly could worsen IQ. Seems reasonable. You don't have that proof yet. This is a longer term project. What I can tell you is that the properties of the graph. And this is where it gets very interesting. So what we found is actually that there are two types of lobes. And every individual has both types somewhere in their brain, and every lobe has both types in different individuals. So, but nobody has all of one or all of the other. So when you look at the frontal lobe, for example, in this individual, what we see is in the columns, this is every possible brain surgery we could do, okay? So in this case, this is doing no parcellation removal. This is removing one area, two areas, etc. What you see in this brain is it's stepwise, meaning there is no combination of 5 that is better than 2. It's always better to have 2 areas removed than 5. Now, this is a different individual, same analysis. So here, there are these little non-stepwise jags. So what this means here is that there are combinations of 5, where it'd be better to remove 5 parts of the parcellations than 2. And this translates fairly far up, and you have to get to a large number of parcellations before this effect disappears. And so what this means is that in some people, it only matters how much you remove of that lobe, and other people, it matters what is removed. There's hot spots. And this is, again, a potential explanation of why we have different cognitive results. That's a clinical question. What we can show is that this mathematics, it's pretty consistent. There's a lot of variability between individuals in this. So I hope everyone, I've kind of taken everyone on a whirlwind tour, and we'll do a little bit deeper dive into this, but how do we utilize this, and what is it useful for? Well, there's a lot of things that you can do with Connectomics that we've never really been able to do before. One of which is, as you look at the reparcellation technique, there's always been the question of, what did we remove at surgery, right? And in the past, what you would do is you would take this, overlay it on this, and if you were sophisticated, you could figure out a way to what tracks were separated. You can make an educated guess, or more commonly, you'd say lessen the parietal lobe. So, you know, you do the Broca method that he did 150 years ago, where you figure out what's the overlap between these people. It's not a terrible way to do it, but here's a more sophisticated one. One of the challenges is that when you remove this tumor, the brain is going to shift. And so this cavity is not going to reflect what the same position in space as the pre-op. But in an area that's topologically invariant, by that I mean that it's robust to deformation, when I remove this, the tracks also shift in a roughly proportional fashion. So what this means is that you can take the pre-op, subtract the post-op, and get a map of difference. Another thing that we've been working on is a number. How do you put a number on a network? How badly is it injured from either the disease or us or both? And how do we know when it gets better? Because again, we do know people improve by decompressing networks indirectly. And so how do we measure this and validate this? And again, if we're not measuring this, how do we even know we're saving these tracks? How do we even know what we're doing? And so the network impact score gives us a potential ability to compare between individuals. And then you get into the interesting question, right? So if I know what I cut out and I know what happened, how do I control for the massive complexity? And this really raises a question that is at the fundamental basis of how we think about knowledge as doctors. So this is a picture of my wife with Grammy Award winner Brian McKnight at a fundraiser. And think of it, would be possible in our current paradigm for these two to be randomized against each other. But obviously, they're very different people with lots of different potential changes. And probably even if they were much more similar in stature, race, et cetera, they still would probably have differences. And of course, you throw a brain tumor in slightly different locations, we know that gives a difference. So what are we doing randomizing these people against each other? Well, we didn't have anything better. But if you think about data-driven neuroscience, a better way to put this is that you basically use themselves as their controls. And how you do that is with machine learning. You make a virtual data version of themselves. So what I mean by that is we take my wife's connectome, We study what's wrong with it. And then we utilize machine learning to say, well, okay, is this person doing well compared to what we would expect them to do? And that is, again, halves the number of patients. It speeds up discovery and is more valid. And these methodologies exist and are actually doable right now. And how you do that, again, is enterprise-grade machine learning. You scale this. Now, another thing about it is, let's say you wanted to make your hospital into a research and data machine. How would you do it? And how would you basically have it to where everyone who walks in the door could be studied with data? Because ultimately, we all kind of realize that's probably the best answer. Well, some of this is you need to extend people. And one of the ways you can do that is you make it so you don't do complex chart reviews anymore. So we created a tool that's basically trained to read a medical record like I do from text. And first thing we did was said, okay, don't study things that are low yield. We also taught it to go read the record and put things in specific places. It also works in Chinese. And it knows medical terms. It knows that no history of cancer is different than cancer. It looks around there. It knows that glioblastoma is a diagnosis and craniotomy is a treatment. As well, and this is actually an idea I got after talking to Sean Grady at UPenn, which is that it's very difficult to get neuropsych on a lot of these big scale studies just because neuropsychologists are busy and they're scarce. And how do we get at least some neuropsych data on everyone? Well, it's simple. Again, if you can train a model that can turn voice to text and then utilize things like convolutional neural nets or other methodologies to try to dive in and say, well, what does aphasia look like? Can we get it to score it on its own? And again, our prototypes say that the success rate of that is about 92%. So this is a product that we expect to be coming online here in a few months. And so then what you basically would do in the situation is you build the cloud architecture to get all this data into a database, you use machine learning to identify clinical scenarios at scale, and then basically use this to answer questions, linking clinical information to connectomics. So I hope I've given everyone a look into the future of why connectomics is important, why I think that we really need to be paying attention to this, and ultimately, industry, meaning banks, meaning Google, they're using these technologies for far less meaningful solutions than what we are. And ultimately, the techniques are very advanced and robust, and often the people who are doing this are in industry. That's where the expertise in these kind of topics are. So what we did was we basically repurposed these people towards tackling real problems that matter in the world, using better data to make better doctors, and putting data and decisions in ways that are comprehensible to doctors at the center of our decision making. And the Connectome seems like a very valuable place to start. But without an annotation of what the significance of that scan is, then it's only going to be so useful. And so we've basically created solutions that can do this end to end. So I'll quickly look and see if there are questions here. Okay. If there are no questions, then we'll. You're about to get that level of skill. I'll show what that's part of this course. We try to make it as easy as possible. So when asked what level of skill, you're about to attain this. That's actually what we're aiming to teach you guys today. McDermott? Oh, Q&A, okay.
Yeah, that was me.
Yeah. So no, it's actually part of the Overmind product. The Overmind product is a full end-to-end research package. One of the nice things about a cloud solution is that you actually always get the most up-to-date version with all the solutions. So one of the things about it is that the entire package is designed to be a research and data generating machine. So it actually is, it's all end to end. And as new features come out, we add them in different formats. The FDA products, on the other hand, will have more, you know, refined boundaries because obviously there's some regulations on that. And we'll kind of show you how we've separated that out. But yeah, the health record product and eventually the neuropsychology will all be built into the cloud product.
Okay, then how's the FDA reacted so far to the cloud-based analysis of the medical record?
Well, the answer to it is that's not inside the FDA because it's for research purposes. So it would be, so we haven't brought that up, but they don't care so much about cloud as long as you have the cybersecurity stuff in place.
So it's institutional then?
Correct.
Okay.
Now we have enough cybersecurity. Remember that one of our main first markets is in China. China has its own separate cloud. And so when you go to China, you think about cybersecurity very, very seriously. So the standards we have are at top of industry. Time, resources, etc. Implementation, depending on the situation, can probably be done in a few hours, depending on every hospital is different. But essentially, it's setting up an account and building an API into the hospital architecture. There's also an online version, but most hospitals we found generally want to have a closed system. So resources relatively low impact on us. It's fairly easy. The biggest challenge is actually getting hospitals to agree to it. Simulate clinical results in DBS simulation. Basically, we can target it. You can study how the basal ganglia is talking to other areas. And there's a few things that we're working on that, again, we have to file the patents on, so I can't talk about them right now, but we have tools. In the future, we'll be able to you'll be able to look at what you're planning on doing in the Connectome and simulate using machine learning what the impact is on the Connectome. We have some prototypes of that now, but if I talk about it publicly, we'll ruin the patent. But the answer is yes, that's in the future. We do repetitive TMS called Theta Burst. And so Theta Burst, we do it for therapeutic purposes. It has about 140 randomized trials. Neurosurgery is new. So it's not new to do it for repetitive purposes. It's new to do it without having a specific target ahead of time. As far as cognitive improvement, we'll talk about it. There are randomized controlled trials in Alzheimer's. There's randomized controlled trials in all sorts of things. And there's also, I think there's 15,000 papers on TMS for various things. There's also a meeting about it. So it is, again, you could get into the weeds about it, but it's at least something that we should be looking at. So in the interest of time, we'll have more time to take questions here. But after you see this next lecture, you'll understand why we're moving along. So one of the things that I always have this lecture second. The first lecture is to talk about what Connectomics is all about. And the second lecture is we're here to basically dismantle how you think about how the brain really works, because probably, I haven't had anyone call me out on this, but most of you are not thinking about it correctly. There's a lot of things that I was taught that have been proven to be outdated. And there are a lot of better ways to think about how the brain works in terms of networks. And so in order to really take advantage of what we've created, it's important to really understand how the brain works. And so the first question is, how does white matter matter? Well, we talk about white matter, not because that we're particularly concerned about the IFOF on its own right. No one's ever said, thank you for saving my IFOF, unless I told them I made an effort to save that. What we care about is function. That's what patients care about. That's what we care about. And we look into white matter as a means to an end. And as we begin to get more sophisticated in how we think about white matter, we need to recognize that not all white matter is equally important. We know that. We know there's parts of the brain we can get away with stuff and parts that we can't. And get away with stuff is something that's a moving target of how, as we improve our outcomes, the idea of not paralyzing people who came in the door okay in a permanent fashion is something that is a lot more achievable for most people who are doing sophisticated glioma surgery. What we're talking about is how do we go further than that? And ultimately, saving function means saving brain networks function, keeping things working in a way that's effective. So what are brain networks? Now, there are 100 different ways you can talk about this, and this can be a whole lecture by itself, just the slide. But basically, in short, networks are parts of the brain that are not in immediate continuity, that are firing together as a unit, meaning that they're correlated, meaning that they're functionally connected. These are all synonyms. Networks that are firing together are usually wiring together. Most networks, when we've had an identification of a network and mapped it to tractography, they have a connection between them. Now, not everything that has a connection between their fires is a network. Sometimes there's things that are connected for the sole purpose of making them not talk to each other. It's fine. But most of the time, if something is strongly correlated, when people have studied this, that these networks serve a common function. But how the common function is usually not a pure function. So if you ask what the default mode network does, well, it does a lot of things. And basically, it's just generally lots of things in cognition. It's not really a relevant question. What it is that the DMN areas are probably doing a common set of operations, or they're communicating for some various purpose. And often when we look at really sophisticated higher functions, and I'll show you an example of this, they're mixing parts together to form a cognitive combination. Furthermore, they're not all equal. So networks lie in a hierarchy, okay? And some networks sit on top of that hierarchy, and we're going to talk about those first. And I'm going to first start off by going through the easiest explanation of the networks and their anatomy. And then there's going to be a twist. And I promise you, when you see this twist, those of you who are anatomophiles are going to be as surprised about this as I was. So how many networks are there? And the answer is anywhere between 7 and 162, depending on how fine and granulated you want to call a network. But in general, there's basically seven guys who explain most of the variants of all the other parts of the brain. There's the sensory motor system. That actually includes auditory cortex. They all fire with the motor cortex, interestingly. The visual system, the central executive network, the default mode network, the salience network, the dorsal attention network, and the limbic system, and the limbic cortices and paralimbic cortices. It's like orbitofrontal. Now, there are subdivisions and then subdivisions of subdivisions, and you could get very complicated in this, but for the purposes of putting your foot into the pool, this is a good way to think about it. Now, a network doesn't always equal a function. And in the current version of the software, we have them on the same menu, but in the one that's going to be updated in about a week, we're going to separate this out a little bit better. I spent some time reorganizing the atlas over the last few weeks to really make this separated out. And basically, the way to think about it is networks are the instrument types. So, for example, the DMN is the brass, and the strings are central executive. And how different instruments play at different times is how a music happens. And that's how cognitive function, the best way to think about it. Again, we've talked about this, and we've made an effort to put everything into this scheme. And so I won't go into all of this because, again, I've tried to teach this in one setting before, and it's too much. But I'll highlight a few of the really important ones. And these are the ones that I tend to look at when I pick TMS targets or think about surgery. So at the very top of the hierarchy are what you could call the control networks. And these are the networks that actually control the function of other networks. And if you look at the variants of networks in the brain, most other networks can have their variants explained by what these networks are doing. Now, what's come out of the last 20 years is an extensive literature about how these networks talk to each other and how they drive global function in the brain. So the default mode network is your kind of internal monologue. The central executive network is what happens when you're doing something actively. And there's a third network that was discovered about 10 years ago called the salience network, which I think is extremely important, and we can talk about that. And its main goal is to determine who's running the show. Most importantly, that these guys are not supposed to be functioning at the same time. In fact, part of mental illness in many cases is these two networks talking to each other inappropriately or not synchronizing in the way they're supposed to. And I have literally attended a meeting about resting state brain mapping where for an entire day, everyone got up and mentioned the DMN in the talk, a clean sweep of a whole day. So and this was a talk mainly about talks about mental illness. So if you look at them, the default mode network is really centered in large part around the cingulum, at least its core. And if you look at the cingulum bundle, people have spent a lot of time, we all are familiar with this bundle, but most people didn't pay attention to all this. And notice that it tends to be more smooth here and a lot more jagged here. And as you look at this, this is the map that we made of the cingulum. It's a lot more complicated than this, but these are those two little, flare out portions. It's also important to note that that area there is the posterior cingulate in the precuneus. For example, that's called precuneus visual area. And it's impressive how much of the cingulum talks to that, how much intercommunication. We also know that this is the most functionally connected area of the human brain. So there's no other part of the brain that has more areas that are driven by its correlation than this part. And it's not really a part that we spend a lot of time thinking about, but it also probably explains why people with splenium butterfly gliomas have pretty significant cognitive problems. So the core of this network, and I'll explain what this means later, but the core of this network, there's a large posterior cingulate component, there's an anterior cingulate component, and there's a lateral parietal part. So anytime you see these three guys, you're looking at DMN. And pretty much, if you look at the different ways of looking at functional correlation, this is the most consistent network in the brain. Almost everyone has one. And there's even studies that show that if you don't form a DMN, you're probably in a vegetative state or doing very badly cognitively for sure. Again, it's kind of the blackboard of your mind. The salience network is a middle cingulate and anterior insula, okay? And it's hooked by the frontal ascendant tract, which probably, as you'll see later, explains its role in language as well as a lot of other things. Interestingly, it's thought that the salience network is overactive in a lot of people with chronic pain. And also, they believe that the salience network is part of the treatment of depression with TMS. And then you have the central executive. It's kind of a little more complicated. It has a frontal polar part, this one area called 8C, which is a really important part of the brain. And this area here in the supramarginal gyrus called PFM, linked by parts of the superior longitudinal fasciculus. And here's an idea of what they're basically doing. So again, DMN, things like theory of mind, your sense of self, free will, for example, imagining things that yourself doing things, episodic memory, most mental illnesses, and a list that can go down 5 or 6 slides if you wanted. The salience network, coordinating responses, switching between networks, emotional regulation, again, probably part of fibromyalgia in some degree. Central executive network, working memory, control of attention, focused tasks. We kind of know what its executive functions, right? And the dorsal attention network is a network that's involved in sustained attention maintenance. And so this is not a pure cognitive network, but you can't really do a good cognitive task without engaging the DAN. You can't really read, you can't do a math. So this thing shows up in a lot of these things. There's also a second ventral attention network, which is generally switching your attention actively. We'll talk about that in a little bit. So the question then is, how does this link to the medial frontal syndrome? And about 4 years ago, I published a series in JNS where we looked at anterior butterfly gliomas. And we found is that if you preserve this axis, and originally we thought it was purely the DMN, but we now know it's probably this axis, that these patients actually did okay. Now the posterior ones are a little bit different and a little more complex, but the anterior one's really simple. They're wrapping around this system. And this probably gives us an idea why things like ACA stroke cause abulia, or why bilateral medial frontal injury causes a akinetic mutism. And there's other people who've mapped people who have akinetic strokes to this area too. It's actually a paper called the Connectomics of free will in PNAS. And again, all of these line up with the idea that preserving these axes, particularly the medial frontal component and its connection to the SMA, because it shares part of the SMA, and again, I'll explain this in a second, is important for getting out of neutral gear. Turning to motor systems, it's important that we note that if you have a motor cortex and you resected everything on both sides of the sensory motor cortex, you're paralyzed. So you have to have the ability to not only have the motor system connected to the spinal cord, but drive it. And so into that regard, there are premotor systems. And it's important to note that they have a very kind of bouquet of flower shape arrangement. There's at least 2 of them, dorsal and ventral premotor, as well as the SMA, which we mapped to the Glasser as 4 parcellations. This one called SCEF, superior frontal language, that should explain the mutism of SMA. And these are the 6MA and 6MP are motor planning areas. And we'll come back to that. The visual network, a little bit less interesting. It's just the occipital lobe as we would expect, and all parts of the occipital cortex for the most part are some part of the visual network. This can be subsetted into subnetworks, depending on the dorsal and ventral stream or the primary, but for the most part, the anatomy is simple in that regard. What's really surprising, what we learned from Connectomics, is how much of the white matter of the brain is dedicated to getting areas of the brain to talk to the occipital lobe. In fact, most tracks have something to the visual system at some point. And when you get into this, why is that? Like, why do so many areas? And what you would first think is that this is sending information from the occipital lobe to the frontal lobe to act on it. It might be doing that, but if you actually look at what part specifically of the occipital lobe that are connected, it's actually probably not what's happening. What's actually happening is that if all the visual information was processed at all voxels, all pixels of the retina, that the visual system, in order to do this computationally, would have to be larger than the actual size of the brain. It's not. So we know that how it really works is top-down orderly regulation on both salient cues, either cognitive salience or visual salience from the bottom up. And this determines what gets processed and what gets ignored in the visual system. So two tracks that are mainly aimed at doing this, IFOF and ILF. Now, when you get into this, and we'll talk about what IFOF's doing in the next section, but again, a lot of these connections, not all of them, a lot of them are going to V1 to V4, which if you remember neuroscience, that's whether the line is going like this, or some higher order shapes. But these aren't high level object recognition. So most likely what these tracks are doing is the frontal and temporal cognitive areas telling the visual system what to pay attention to and what not pay attention to. And that can have a significant cognitive component to it, because again, it determines what's relevant of how you perceive the world. But it's not necessarily that information is flowing in this direction. Getting into language, this is what I learned in my medical school residency. I believe this for a very long time. And it's not totally wrong. We know that these 2 areas do have language areas. But a lot of people have begun to postulate what were called 2 pathway models of language. And there's a lot of these. Most people are probably familiar with Hugh Defoe's model that involves the arcuate SLF complex doing phonemic language. Most people agree on this. And that the IFOF being the semantic component. I've kind of shown reasons why I think that there's some challenges with it. It doesn't mean it's not doing something in language, but it's not so simple that it's carrying visual information to area 45. Other people have postulated things involving the ILF and uncinate, going to the temporal pole as an intermediate. There's very good data to say that the temporal pole is part of this process and verbal memory. And there's a very interesting model that I'll show that I think is really important in this, which is by Marco Catani in Italy. Now, if you look at areas of the brain that are involved in meta-analysis and language, it shows first that there are 2 streams, but the 2 streams are actually first both phonemic. So again, you have the complex Wernicke complex, and of course you have this what we call Geschwin's area. And notice that this is part of the central executive network, and also 8C. So the executive areas are part of language. They play a role in that. But the first stream obviously is the one we're familiar with, the one that goes to area 44. But then you have this other stream, and the other stream involves this area 55B. As well, you have components from the SMA communicating via FAT to 44 and its components. And again, what this shows is that our initial language maps were just not even adequate to explain everything that we've seen. And if you, again, for those of you familiar with Eddie Chang's work on language, if you watch his videos of different parts of the ECOG grid flowing, everything along the strip is activated in some aspect of his language task and along the motor cortex. So it's kind of oversimplistic to say that there's this magical area and this is everything of speech and language. It's not really like that. And also, what's important as neurosurgeons that we start talking about speech and language is two different things. One is cognitive and one is motor. So for example, motor function of your hand is different than apraxia, which is cognitive control of motor. And language and speech have a similar relationship. This is a case report that Eddie and I published together recently in neurosurgery. It's hard to get a case report into neurosurgery, as I'm sure most of you know, but we felt that this was actually a good place for it because what we found as we started studying 55B, and he had recently published a Cell paper showing that this was probably a motor cortex for the larynx. I went into my case file and found this case from a long time ago where we took out a very small glioma and, you know, again, didn't cut any of the deep tracks. They thought everything was fine. And in the long term, this guy is an accountant, can type a very complex email to his clients, can name everything you could expect, but he can't phonate, and his phonation skills are off at the larynx. His mouth and tongue all work normally. And so this really begins to argue that 55B on the left is a part of the language system, and it's a real place. So as we began to look at this model has gotten a lot more complicated. So of course we still have the traditional flow to 44, but we have other areas to 55B, which is different. These areas don't talk to each other. You have components of the SMA that are part of initiation. And furthermore, you still have the question of how to verbal memory and what is the second stream. So let's do a little bit deep diving on this. Again, it's important that the semantic stream, or whatever you want to call it, the verbal memory stream, the stream that's affected with temporal lobectomies in some patients, et cetera, is a language problem. And one of the things when I became really interested in studying this a few years ago, what are we doing wrong? And why does LIT seem to avoid this in some cases? And why does selective amygdala campectomy sometimes cause this when we're not taking out the lobe? And my best theory on this is this. So if you look at the functional connectivity map, and you look at this area TGD, which is the biggest portion of the left of the temporal pole, on the left, it has this little strip. This is right along the superior temporal sulcus, okay, that links you from areas that are clearly part of the language system to the temporal pole along this little strip here. And of course, if you follow the uncinate, you see it right to the canonical Broca's area, 44 and 45. And you also see this, and this. That's DMN. So this is probably part of an extended DMN pathway. So again, while you have things like the ILF and the uncinate carrying information from the temporal pole, this may be utilizing this pathway to talk to the visual system, get its affairs in order, and match that to a name. But it also raises the point that the part of the name matching arises on this Catani pathway. And when we started looking for this, we found that there's this unique set of U fibers. I've never seen this anywhere else in the brain that parallel the sulcus. And this is probably why you see this as some kind of serial processing system. So it's at least these two pathways. And again, so you have here, you have your phonemic, you have a complex relationship between ILF, uncinate, temporal pole, and then this kind of superior temporal sulcus accessory language pathway. And we have this in the software too, for people who are interested in this. It's important to note that then language is, as we expect, a complicated function. It's also important to note that the auditory system here has a direct link to Broca's area independent of all of this. So you have polar components, you have accessory components, you have auditory components, and you have the classic phonemic part. And what these all have in common is that all of them on the left side of the brain are part of the default mode network. They're all DMN. I'll show you evidence for that. So where does IFOF fit into this? And is IFOF left out? Because it doesn't really connect any of these areas directly. Well, it's possible, but it's a complicated relationship. So this is our map of IFOF. And as you can see, you know, you have 45 in here, we knew that. And you have other areas that are around there. But you also see there's a lot of areas that are basically, central executive areas and DMN areas. And what they're mostly talking to, the majority of these connections either are to early visual cortex, where there's no way that the higher level executive areas probably want to know that the line is, vertical or horizontal. And these are areas that are either high level parietal areas or areas involved in spatial recognition of position, like the WARE pathway. You don't see a lot of object recognition areas that directly are talking to the areas that we're interested in. So it's possible that the cognitive areas influence vision through this pathway, and thus it has a role in language, but it's not as simple as the visual information being carried to Broca's areas. It's just not how that system seems to be wired up. Again, it's possible to model more complex functions also using some similar techniques. So here's our map of the praxis system. You can see that it, again, involves different areas and how they talk to, for example, the motor system, how they talk to parts of the salience network, et cetera. And I don't have time to go into this very complex slide, but you see that it is, you understand why some people would have apraxia with aphasia, but not everyone would. Now, what is the right side doing? Well, of course, the SLF didn't grow there for no reason. So we tracked this and looked at patients in different studies that had neglect. They're using the meta-analysis technique. And as you can see, this is following the arcuate and SLF. What really gets interesting is we say, well, who are these areas? What is it connecting? And we can look into this and have an answer to this. And this was very complicated for me to look at. It took me a long time to realize what I was seeing. But what I eventually figured out was that we had a mixture. You had sensory motor, auditory, you had parietal areas involving dorsal attention. You had parts of the default mode network. This is an analog of Wernicke's area on the right side. This is the piriform cortex, that's olfactory. And you have areas that involved in frontal eye field. So what this is these are the fibers that join up these networks of different parts and get them to bind everything into a common world. At least that's our theory. And when we started looking at the dorsal attention network, it seemed like, well, that's a reasonable candidate. It seems to follow the same path, which again, dorsal attention is areas around the frontal eye field, the intraparietal sulcus, so think twice before you put a cannula down that, and higher level visual areas like MT, MST, and a few other visual areas. And that's a relatively simple network. It's bilateral. There's also a right-sided network. We thought, oh, this has to be it, but it's not actually. They're very close to each other, but they're not in the exact position. So while it could be the ventral attention network, it doesn't seem to line up with that very well. And neglect probably is his own system of getting different parts of different networks to work together to serve the common task of joining the world up. And when we start talking about cognition, like math, it's never going to be a pure network. It has visual components, semantic components, dorsal attention. And there's this core in here that we found that really aren't clearly part of any network. They're kind of affiliated with certain things, but they're not core parts of any network. And so it's really these guys, the core, that links these guys up and gets them to talk to each other. So let's come back to networks. And the next thing I'm going to show you is, I think it's absolutely mind-blowing when I really understood this. So this is a paper from 2011 out of Harvard by a guy named Randy Buckner. And it's been around for a long time. And I recently saw a talk by him where he showed some things, and it really got me looking into this data a lot. So what you're looking at is a map where they said, okay, every part of the brain has to be part of 7 networks, and based on who they're correlated with. And so, for example, sensory motor, vision, the limbic system, the central executive in orange, the DMN in the sort of reddish orange, salience is purple, and DAN is green. Okay, so notice that there's areas outside the core network. For example, that area is outside the core network. This is not a classical CN area, et cetera. This just means that these areas are highly correlated with it, but they're not absolutely core to it. They can affiliate differently if they want. So they're mostly CN, but they can change teams in certain circumstances. Now, one of the things that's interesting is this seems like a random map, and to help you remember it, I'm going to make it non-random. So one of the things you can look at is if you look at the interhemispheric fissure, there's sensory system, there's salience, there's executive back again, DMN. Come on to the other hemisphere. When you look at this onto the surface, you see that there's this sort of pinwheel pattern, DMN here, DMN in the parietal lobe. And again, it makes this sort of S-shaped appearance. Now, let's look at another network, CEN. Okay, there's the same pattern. There it is on the convexity. There's in the parietal lobe. There's in the temporal lobe. Okay, now we look at this extended network again, salience network. There we go, same exact situation. And you see that some of these components are very small, but it has this sort of S-shaped pattern. And the dorsal tension network doesn't follow all of that. It's an older network. But again, it's kind of striking. And turns out that that ordering, and that pattern is held deeply throughout, far back, at least in primate evolution, and probably further back. So at least back to marmoset, so as far back as you can go in the primate kingdom. This repetition, and most likely this is going to be repeated in other animals. So the next question is, okay, well, how is this, since it's patterned like this, even though it looks random, it's not random, it's just a little bit chaotic, but it's random, not random. What about the cerebellum? Well, turns out that the majority of the hemisphere is not doing motor. It's actually functionally correlated with these networks. And when they looked at this, they found that if you were to look at this in the coronal plane, it looks kind of chaotic. But when you look at this in the sagittal plane, it's anything but. So there you have motor, salience, executive, DMN. Then it mirror image flips, DMN, executive. There's the dorsal tension. Yeah, it's back here on the superior surface too, if you look at it. Salience and motor. And it turns out they're basically also represented in the flocculus again. So this argues that this is part of the patterning of the nervous system. And it extends all the way to the basal ganglia. You see that there's relationships that are repeated. Okay, so again, what this shows is that the organizing principle of the majority of the association cortex, the majority of the cerebellum, and a lot of the striatum is based around functional networks, not based on anatomical relationships. Now, if you want to get deeper, we talked about core networks, and they still exist. So if you basically decide, okay, instead of dividing this into 7, I'm going to subdivide them. Well, you get the networks fragmenting. So for example, there's your DMN cores, that yellow guy. But then you see that guy, that red guy, and you see that along the axis of the superior temporal sulcus and in the parietal lobe, that's the language system, which is part of the DMN. If you go back, you look at this here, language is part of the DMN. If you were to look at also the auditory system is its own system and is also part of the DMN. So if you separate them out, you can separate them into 2 different networks. And then there's this final part here where the DMN is heading into the hippocampal structures. And again, that's also part of the DMN, but it's a different network. The central executive network has a similar set of clusterings as well. And again, this will be in the next iteration of the atlas. So when getting back to the 2 streams, you look at this and you say, okay, well, there's your auditory system. There's your accessory system, the accessory language. And then you also have the phonemic portion. But the next question is, okay, well, how does hemispheric asymmetry rise out of this? And of course, we can't answer that question specifically, but I will note that these maps look very similar. And this is that same map, almost identical, done by a different study, different group on a very large data set, showing that these parcellations link up almost exactly to the Buckner paper, which is really interesting. But this is in Glasser, so we like that obviously because it's on our same scheme. And what you can see is these areas look mostly the same. I mean, the motor system looks the same. The question is, where are they different? And this is really interesting. So there's 44, DMN on the left, central executive on the right. That's 55B, DMN on the left, salience on the right. Then you have things like 8AV, and PGS. Those are our anxiety targets. We pretty much almost always see that abnormal anxiety patients. DMN on the left, executive on the right. Another thing you can notice this is that, let's talk about motor planning areas. Like, why are they planning areas? Well, they correlate with motor, but actually parts of them correlate better with other things. So if you look at the SMA, there's parts of the salience network. Those are 2 of the parcellations right there. The superior frontal language area is, DMN, because it's a language area. and the sensory motor. So the SMA is where these complex networks go together and how the motor and areas that turn on and off these functions meet. It's a mixture. What about the premotor areas? Well, if you look at the dorsal premotor area, it's a sensory motor meeting CN, meeting dorsal attention. If you look at the ventral attention network, DMN, CN, that's Broca's area, that's things next to Broca's area, dorsal attention network, salience network. The area here, the 6R, which is right next to where the generation area of the speech arrest site, all these areas are clustered around so they can exert control over this. And so what we're really showing is that when we talk about planning, these networks, the greater part of these networks, come on this to exert a common goal. So anyway, that's a whirlwind. And the next thing I'm going to do is I'll actually show you how you can show this in the software, but I'll first answer some questions. We have a paper that is under review right now on that topic, yeah. But we don't have extremely detailed cognitive experience.
Yeah, Mike, we don't know what the questions are, so when you answer.
Oh, sorry. Oh, yeah, sorry. So on the McDermott's question about mentioning mutism reminds me to ask whether you can look at connections in the cerebellum. And the answer is, obviously,
you showed it. Yeah.
Yeah, there's a DMN composition of the cerebellum, Yeah. So yeah. The 55B patient was the deficit immediate. Well, the answer is yes. They woke up with language issues, and of course we thought it was quote unquote swelling. We didn't have an answer. I didn't have an answer for this for years, so I just kind of said, sorry, I have no idea. Now the question about can you do safe operations? Well, obviously you can. You just have to make sure you do your homework. What the question really with it is that how do we ever get away with surgery? Well, obviously there's a mechanism, and we can start utilizing this to try to figure out what is a better mechanism. And the truth of it is this: I always told my residents, if you have a glioblastoma in your motor cortex and you're paralyzed, the only thing worse than that is still having the GBM there. If you're not going to save motor function, at least get the oncologic benefit. So you may make a decision that this is not salvageable, doesn't oncologically make sense. If somebody has a minor, and that may be a decision you and the patient make together, but now you're doing it in an informed way and not accidentally having it happen. What we don't want to have happen is after the fact, you have I have no idea that happened. And we can never learn if we don't measure. If we don't measure it, we're not going to learn.
Yeah, have you seen in some of the patients you've operated on use the analysis of their brains after the surgery that the functional networks are altered after?
The answer to it is we have, I can show you examples, where there's functional network alteration. One of the challenges with it is this is to really do this in a meaningful way, you need to have enough data and analyze enough data to realistically start to find patterns in the noise. And so what we know that there's alterations for sure. I mean, I can show you. And in many cases, I've been able to stare at it enough to where I can convince myself that seems to make sense, right? But of course, there's things that we don't know, and we want to utilize, better standards to take that forward so that eventually you can say, if you cut this and this is what's going to happen with reasonable certainty. And there's so much of the brain we can't do that on now. I mean, the frontal lobe, we always thought you could just go hog wild in there. And the answer is you can do a lot without devastating people. But we, of course, know that if you ask questions, you see that you're not doing as well as you think you are. Going through some other questions here. So the meta-analysis method. I'll explain the meta-analysis method. So basically how it works is, let's say we take every fMRI study that's ever been done, and how do they report their results? Well, if they're doing it correctly, they report them in a coordinate scheme, usually what's called the MNI coordinate scheme. So they would say 55, -6, 10, or something like this. And what that means is that you can take those across studies and combine them using a methodology called ALE, or Activation Likelihood Estimate, which forms a Gaussian around those points in three-dimensional space. What we then know is we have the the map of who those guys are in the HCP in normal brains. And so if they're occupying the same space, they're probably, that parcellation is the most likely candidate for it. Now, having said that, we could find out that our maps are not perfect, and fixing that is actually involves changing something on the spreadsheet, and it could be fixed in 10 minutes. But right now what these are the best models that we have for given the existing literature and data. To get to, can we use this information test with TCDs for planning a resective surgery? Well, again, that's the long-term thought process. And it's one piece of information. It's, I think, a pretty good piece of information. And it can often point to things that you wouldn't really be able to answer in the operating room in a meaningful fashion. So, and one of the things that we want to get into this, and again, my background, if for those of you who don't know me extremely well, is I do tumor surgery, and I did, I think, 1,000 gliomas or something like this in Oklahoma, of which I did DTIs on almost every single case, and many of them I did awake. One of the thoughts is that as we begin to gather more information, it will get very difficult to justify not having this information. As we know, well, right now we don't have, I can't tell you, if you don't preserve the central executive network, then it's going to be cognitively destructive. That's a clinical question. It seems like a good thing to think about right now. And over time we'll learn about this. Getting to Nitin's question, I do have a question too. Can you elaborate on your thoughts about the temporal pole and dysnomia? We published a paper in Brain last year where we imply that it's really the mid-fusiform cortex is critical for this, and now we need to prove it. The answer to it is the temporal pole dysnomia question can go on for a very, very long time. And to really do it justice, Marcel Musalam, I've seen him give an entire talk at OHBM about this. His model about the fusiform would argue that it's actually the ILF that is part of dysnomia. And that if you actually trace out the ILF, there are clearly areas that go to visual recognition areas. And so it would make sense if you told me that that was part of the problem. I put it in my model. However, I do think that there's, the big question is, where does the word come from that matches that to that? Because there's not probably a lot of semantic knowledge in the occipital lobe per se. And so it may be that the temporal pole is doing a comparison between visual information and semantic information, and then sending that by the uncinate to 45 and 44 where they make a decision on it. That's the Musalam model. I think that, honestly, the biggest thing about it is that these are questions that we can answer and get better information, but it's going to require a lot of data and a lot of careful thought on it. And what we're probably going to find is that it's all of the above. Again, it was simple to think that we could summarize something as complicated as human language with a single connection, i.e. the arcuate. To answer Kostas's question, are you restoring or promoting new networks? Well, obviously, if a network is cut, you're not going to put it back in the head. So if you've cut the corticospinal tract, TMS is not going to solve that. If you cut the arcuate fasciculus, you might be able to get a collateral pathway to do some of the function, but you can expect that problem is going to be a long-term problem. What you're really saying is, in some cases, and I'll show you examples, parts of the network have discorrelation. They mean they're hyper or hypocorrelated. And what we found is, in some people, if you turn those areas up or down based on what we see in the connectome, we have seen some significant improvements. And what we would assume is that there's a combination of functional and structural or structural disturbance, and that we can answer that question, and in some cases gain at least a little bit of function, or in some cases a lot of function, depending on the patient's context. But the thought process is, ultimately TMS causes plasticity changes in the brain, and what we think and what we hope is that we're stimulating these patients to rehab. Because if you're talking, you're strengthening your plasticity. Well, a lot of times it's the inability to get started that prevents the rehab from actually happening. And so in the most ideal scenario, in the worst of the worst, we're actually getting them into the rehab cycle meaningfully. How can we get the software, and how can we load the patient information and DTI map on it? Yes, that is the point, and we can get you plugged in with people who can help work that, make that a reality for you. But the answer is, the software is designed to handle and do all the processing, and I'll show you the link that we gave you is to the viewer for it, but it is possible to upload and answer your own data. How long does TMS functionally resolve the targeted network? The answer is we don't have enough data to talk about that meaningfully, but in our experience, in surgical patients, they tend to be lasting. So for example, if you restore someone's ability to walk, then they're going to keep, you know, A, the circuit's still there, and B, they're going to keep rehabbing the circuit. If you're talking about mental illness, it's a different problem. So fundamentally, what they believe the mental illness problem is some kind of thalamo-basal cortical dysrhythmia. So the system, the thalamus or basal ganglia are rhythm generators. The rhythm that they send up to the cortex causes some areas to oscillate together. And if that rhythm is wrong in some way, that there's functional connectomic disturbances that result from that. Now, if you were to think about that and you say, okay, if I stimulate part of the central executive network and I make somebody's anxiety or depression better, what's to stop them from going back into that system? Well, the answer is we don't know how it happens in the first place. What we do know is that the TMS can last for months or even years in some people, and occasionally leads to long-term results, but they frequently need retreatment for mental illness. That's a pretty well-known in the field. One of the things about it is ultimately, if you're talking about you know, once every couple of months coming in for a handful of treatments that are safe and effective versus taking antidepressants, which have their own set of side effects, if it's effective, then none of these patients don't have a problem coming back, and especially with modern protocols like Theta Burst, which we'll talk about, that can do the treatment is 5 minutes long. So you can get it done in a couple of days. Can TMS have ACA stroke 3 months of ACON clipping? Interesting, we have not done clipping because I'm not an aneurysm surgeon. However, I do have a really great case that we're in the process of hopefully getting out the door soon. And it was a patient who lost their medial frontal lobe to a glioma, looked terrible before the surgery, looked terrible after. We did everything, you know, the usual stuff, and he was not even verbal, wasn't opening his eyes. He was opening his eyes, but he wasn't regarding. Basically, worst aconic mute. We thought that he was going to go to hospice. We told the family to go to hospice. They were these religious types where they said, no, Jesus is going to save my dad. Turned out Jesus stepped up big time for this guy. And we eventually, after about 3 months, he was still in the hospital because nobody would take him with his diagnosis and his status. So I just said, why don't we get a resting state on him? So we did. Turned out none of his DMN was synchronized with itself. This is back before we had the software, so we used a much more, you know, blunt sword technique. And when we looked at him, he didn't have a DMN. His DMN didn't functionally form. So we re-stimulated him at the DMN, and he woke up and actually got to the point where he could actually have a conversation about the risk and benefits of chemotherapy. So I don't say that that's something that would happen all the time, but if you think about this as the center of cognition and you don't have one because of his case, structural damage, it raises the possibility that, and ultimately one of the things we'll emphasize is TMS is one of the safest neurologic treatments we've ever seen. It's really safe. I mean, there's lots and lots of class 1 evidence that shows that. It's psychiatrists do it in their office. So given that we're a bunch of neurosurgeons doing neurosurgical stuff like clipping common aneurysms, if you have someone who's in that bad state, why not try it? What are you offering that's better? And that's kind of the thought process that I had when I first started doing this, which was, you know, you have to have a different thought process when you're talking about completely normal, healthy individuals, but it's a little different when you're talking about people you're talking about with ACA strokes who have bad prognosis. If we get a small percentage of DAI patients out of comas, even if it's 2%, that is a huge win for society, given the safety of that treatment. So what I'm going to do now is we're going to give the first glance on the software here. And let me get to where I need to go here. Now, all of you guys got log on to this. In the interest of time, what I'm going to do is I'm going to quickly go through it. This is going to be our first run. And then I'm going to show you brain networks.
Mike, it's a SSG conference in facility.
Oh yeah, I keep doing that. I did that yesterday too. Okay. So as you can see, the software works in Google Chrome. There's no downloads. It's all cloud-based. And when I select here, what this does, and literally, you guys are the first people outside the company to see this. The patent for this went in this week. But what this is eventually going to be is, this is the first level, and it's being rolled out over the next couple weeks, is a method for analyzing and simplifying your data subsetting to get to a clinical question. So as you can see, there's a research mode, which is going to have a number of the machine learning models that we've created, not only for neurosurgery, but other things. This is a very cool tool that I'll show you guys. But for example, we've come up with montages of surgical plans that are automated. So for example, I could just say, I want to operate in the left frontal lobe, and it takes me and makes all the tractography exports. But for the purposes of this one, and I'll talk about this here in a little bit about the QuickMind tool that we're creating. But for the purposes of this course, we're mainly going to go to the viewer. So when you go to this, what it's doing is it's going out to the cloud. Now, over here, when you see in the lower upper right, there's the thing that says load local file or new case. New case is where you would upload your DICOM images. And it has the ability to read the DICOM information and to know what you want to do with it. And so it also, there will eventually be a portal for uploading medical records, and it's possible to API integrate into that. So it's possible that the hospital server could fire directly into the cloud straight off the MRI. So what that means is that getting fMRI DTI data into the surgical navigation system is basically like ordering a sodium, pulling it up and checking it, and then hitting an export button. That's what our goal. And we'll talk about in the next lecture of what the QuickMind exports are going to be and how we pick them. These are kind of designed based on doing some of this. So when you look at the viewing platform here, first we're going to be focusing on the tractography platform. As you can see, that this is a machine learning atlas, this patient specific, and we have the ability to manipulate this in Chrome. The borders are jagged. That's because the machine learning has moved some of the voxels. We know that it reclusters about 3 to 5% of the voxels, depending on who the patient is. And we think that's about right. I mean, we don't think that it should be reclustering 30% or 40%. It's probably doing it wrong. We also know that we've restrained it. So we won't look for Broca's area in the occipital lobe. It only looks for Broca's area about here. And that was an important breakthrough that we had of how to make this actually not do weird stuff. Now, in the software on the left, this is the subsetting pane. These are the tools. These tools here are coming out this summer. So this is a much more compelling visual representation of this. And we'll show you this one. This one is available. We'll be covering that in the the last part of the course. And then this is a graph theory tool. We have all the machine learning parts for this, but it's making a compelling visual representation. And this is a guide, and I'll show you what that does later. On the right, this is your navigation. So this is a standard PACS platform. Now looking in 3D, what you're going to see is basically this. So for example, this is how you can three-dimensionally figure out where you're at. With everything on the screen, it's not as useful, but when you're trying to figure out where areas are, there also are 2D renderings if you go over to this side, but 3D is kind of easier to work with right now. Here are situations of tracks. As you see, it's pulling all the tracks down. It maps about 500,000 tracks. We can display about 50,000, but the machine learning is on 500,000. For anyone's purposes, it will be able to show you what you need. And there's some huge advantages to doing CSD, and you'll see why when we get to that point. This here allows you to pick between the machine learning atlases, which are the conservative and liberal, and the fitted atlas, which is generic atlas. Here, this is a tool for making ROIs, and this is going to be your shopping list of where your exports make. So when you pick an export, and I'll show you how to do that, whatever's on the screen plus the T1 gets put into a bucket that you can then hit. Now this thing down at the bottom, and it will export it to a DICOM for medical imaging or things like this. Down in the lower right, the download the case, this is for power users. So if you're a researcher and you really know what you're doing, this will give you all the derivative files, all the data. I would say that unless you really want to really know what you're doing on this, a lot of times if you're interested in taking on a very big project, we're also interested in helping you take it on. And so a lot of cases, we have access to these files, and we can actually do machine learning on them all over the world without moving them out of the country that they come from. And actually, a lot of our data agreements involve not taking direct ownership. We're kind of like a storage shed for you guys, but it allows us to actually keep that where we're staying within all the data laws and being ethical with how we handle data. So over here, you have your subsetting tool. There's different ways to subset it. There's about 2 more that are going to show up next week, but this is what we have right now. One is network, by parcellation, by tract. So for example, a lot of our friends are here. And then also by region. So if you just wanted to pull the insula, there you go. So any way you could possibly want to do this, we will have it. We're also putting in the extended networks that I just showed. We just finished that a week and a half ago. But here's the simple one. So let's say I just want to do language. Now it's loaded all the tracks. I hit this button, and what it's going to do is it's going to pull the parcellations and the tracks that connect them between guys. So as you can see, there's SMA. This is the frontal slant tract, or FAT. This is area 44, 45, 8C is this guy here. And there's 55B there, right there where it's supposed to be. Also, you see that there's parts of the auditory. Again, the colors are about what type of area the HCP thought they belonged to. So auditory is in red and blue is vision. We use the same color scheme. And what I'd have now, though, is let's say I want to navigate this, and I want to say I don't want to cut this at surgery. What you can do is you can hit export, and you go to language. And what that did is it made an export over here. And if I hit request export, I type, and again, we can set this up where it actually gets this info from PACS, but if it's not API integrated, you have to add it yourself. And what that basically will do is it will make an object of everything on here that's not the T1, anything you created. So you can pretty much create any combination of anything you want on here and export it. Now, if you want to go back to, it's generally best to do things one at a time in this, we found, because again, these objects, as you see, are much bigger than you're probably used to. Now, let's look at sensory motor, right? So we click sensory motor. It's basically looks sort of like this. So as you can see, you have the motor cortex, but also notice it has the motor planning areas too. Now, let's say, for example, I wanted to only see the SMA. All right, well, we have an app for that. So there you go. You can basically turn everyone else off. So let's say I don't want to see these other guys. I want to see that. And I want to see everything that goes into and out of that. Okay, actually, I don't want to do that. Put that on here. Okay. If you go to tracks, there's this thing here. And what in most situations, you actually just want to see what's going between A and B, but you can turn that off. And then in the interest of simplicity, let's turn the right side off. So now what I have is only the 4 SMA areas. And after it gets done thinking about this, it will give us what we need, hopefully. But as you can see, we've got a lot of other things. So let me kind of show it to you here. And I'll put this back on. So kind of re-emphasizing the lecture we just had. So there's default mode. Actually, hold on. Let me just reload this here. So we have default mode, DAN, we have the ventral attention network, the visual system, salience. Neglect and praxis are functions, but on the right side, that's actually one of the things you want to try to avoid. You have the auditory system, which can be interesting for various purposes. And then, of course, this is that accessory language, which if you look at this is that superior temporal sulcus pathway. It also involves this temporal polar area, TGD, this was on there. So it can, there's all sorts of different ways you can basically slice and dice this data up. Now, looking at DMN, when I go to default mode, what I basically have is, again, let's come to this real quick. So as I scroll up here, I scroll up on the axial. As you see, when you get to the place where that's actually located in 3 space, it dives into the brain. This is how you use a 3D model. And you can see in the sagittal plane, anterior cingulate, posterior cingulate, lateral parietal. That's DMN. Now this is core DMN, not extended DMN. There will be a model for extended DMN within a week or so. Looking at another network, central executive. And again, we've modified this recently, but again, mostly a frontal and parietal network. You see there's 8C, this is the frontal pole, and we've taken these parcellations and reassigned them, but this one is the PF1. Bilateral network, most of them are, except for obviously language is not one. It's an asymmetric network. This is your dorsal attention, and it actually looks more obvious on the axial. So this is a typical appearance. They straddles the motor cortex anterior posterior. It's probably an older network than say DMN. Probably lower animals needed a dorsal attention network more than they needed to think about, you know, incredibly complex mental states. And as you can see, there makes sort of an L-shaped appearance. And then actually, sorry, let me go back, reset. Now, again, ultimately, once the QuickMind wizard is complete, some of this will be automated, and it'll be automated by basically what part of the brain, in this part of the brain, what is relevant to the surgery you're doing. But give everyone the last view on brain networks. This is salience, and it will think about this for a second. Or more than a second, I guess. So what it's doing, and again, this kind of highlights the point of why parcellation is useful, is that it went into the forest and it pulled out these trees. So again, the core of this network is middle cingulate and anterior insula. So you can see there's your middle cingulate, and there's your anterior insula, and also the opercular area. The underside of the operculum is actually a different network. And then we'll just kind of do one more, I guess. If you look at neglect, it kind of gives you a little bit different than a language system. It's not exactly the same, but it's an analog. And you know, again, you could imagine that some of these parcellations on the left got repurposed for language. And that's why, again, why you can't compensate. Now, one of the things about it is the guide. And this is something we put in here because I realized pretty quickly that everyone wouldn't know what all this nomenclature was. They don't live in the same world that I did. So we have a way that essentially whatever you have up on the screen, it links you to a guide of what everything we know about this. This is from our supplement. You can see that there's, you know, the resting state connectivity, tractography, what's known about its function in the literature. Now, if I were to change what this looks like, again, it talks about who these networks are and basically updates based on what is clicked over here in the subsetting pane. And you can imagine how long it took me to help organize this for the developers. So anyway, that's the intro to the software. I guess we'll take any questions. And we'll be back to that. So again, if you didn't catch everything, then we can get everyone caught up. We'll have a couple other exercises where we have a little bit more time to go through, where we have cases that are loaded in there. But that's the basic tour of what the software does and what networks look like to kind of reinforce it. Let's see. Okay. All right, well, if no one has any burning questions, let me move on. Okay, so we covered a lot of information, and if you caught all of that, you're an amazing individual, because that took me, I think, 8 years to get all that together. So how do we use this, and how do we use this in surgery? And to a group that is basically subscribing to the SSG, we're going to make a basic assumption that you believe that it's important to not cut tracks. And how do we go past that? Well, I happened to publish a book on this before I even had the software. And of course, I'm not doing this because I make any money off this, but I do think it has some useful tools. And I spent a lot of time writing this to try to figure out how do we use at least tractography. This is before we had Connectomics in a meaningful fashion. And it also has some of the things I discussed in there at a much more proto level, because it was written several years ago. So how do we use Connectomics to make better decisions during brain surgery? Well, I learned about the world in terms of eloquence versus non-eloquence. You're supposed to stay in the non-eloquent part, stay within the tumor, and just don't cut the corticospinal tract. Maybe the arcuate. That was probably a good idea too. And those aren't bad pieces of advice. None of those things are necessarily bad advice. If you do that on a regular basis, you're not going to have terrible outcomes. We're not stupid people, and we know how to stay out of trouble. But I would argue that this isn't the highest level of sophistication that we can aspire to. And so reality is, if you're sitting there, you're a thoughtful person, you talk to your patients, and you're honest with yourself, you are going to notice that you have neurologic deficits that aren't explainable, that they're not swelling, they don't get better. Or they get better, but they're not really better. Like the patient walks in with a cane, you're like, oh, moving all four. And that's a good defense mechanism. I'm going to tell you, it's hard to be brutally honest with yourself and be brain surgery for a living, because your outcomes will haunt you for the rest of your time. But if we want to improve, we need to kind of occasionally live in that world of being harsh on ourselves and improving what we do. And it is without any doubt that there are cognitive problems that we don't admit to. And that may be that it's the lesser of the two evils between the cancer and the tumor. But what we don't want to have is where we do this on accident. So whether we admit it or not, we are cutting next to brain networks. And the subcortical space has anatomy. Even if we don't see it, it's there. So just because we don't see it doesn't mean we have carte blanche to do whatever we want and blame it on, bad disease or things like that. And all of the brain is active. Now, that doesn't mean it's all important. People have gone far and said the whole brain is eloquent. We know that's not really true, and the term eloquent is not really very good at drilling down on this. What the reality is, it's doing something, and the question is, can I get away with what I'm about to do? That's the real question. It's all there whether you admit it or not. But you don't have to believe in tractography, you don't have to believe in Connectomic, you don't believe in anything. It's there whether you know it or not. So there is a truth, and it is knowable whether you choose to know it or not. So where does tractography come into this? And what I'll say first is that you cannot take tractography and drive it off the cliff. It's not going to protect you from doing something stupid. The analogy, though, that I use is Venice. So the Venetian lagoon just kind of sits between the mainland and Venice. And for centuries, Venice was an independent country, actually all the way from the Middle Ages until Napoleon finished it off in, I think, 1811. And it wasn't because Venice was not attempted to be taken over. It was a very rich city. People tried to take it over all the time. But what the problem was, the Venetian lagoon had traps and ways that if you took an army on a boat to invade Venice, and you didn't know what you were doing, you were going to probably wreck your boat. And the Venetians, on pain of death, kept that a secret. If you go to Venice now, this is what you see, which is posts that tell you where to go. Now, the Venetian lagoon is the white matter, and it's the brain, and it's undefined. There's not many landmarks. And if you don't know what you're doing, you're probably going to wreck your boat. And if you go about this in areas that you're not familiar with, you're probably going to wreck your boat. The posts don't prevent you from wrecking your boat. They just kind of give you a framework of what you're not supposed to do, and it makes you a lot safer. And so what DTI and tractography, all these things do, they're not a shield that protects you from a problem. They're not things that you can trust with millimetric accuracy. They're a way to say, what am I basically here to not do? And that's important because nobody, absolutely nobody, I don't care how good of a surgeon you are, is better with less information and a worse understanding of the problem that they're to treat. Nobody. So we don't need a randomized trial to answer this question. The answer is, you're not stupider, if you basically have more information. You can choose to ignore it if you don't believe it in a particular case. So what are we trying to do in a surgery, in a glioma surgery specifically? Ultimately, at some point, whether you do this with a CUSA and suck it cell layer by cell layer from inside out, or whether you do it as a lobectomy, or whatever you do, at some point, there is going to be a decision between what stays and what goes, where you divide what's going, i.e. tumor, from brain. Of course, in gliomas, those are two very vague terms, but the bottom line is you're going to make a cut between what's going and what's staying. And what we're going to do is figure out what's needed to function and cut on the correct side of that. Okay, it's really that simple. And once you've done that, you've made a tumor non-eloquent. So I put these there. These are all from the book, and these are disconnections that I spent some time working through, and in my experience seem to do okay in most situations. Okay meaning you at least don't cut across anything big and leave obvious deficits. Now, this isn't cognition. Cognition may not be down to a single track or a single place, as I pointed out, but this avoids things like language, motor, things like this. And right now, this is the best models that we have until we get better models that could give us more detail. Maybe we might find out in John, who you're about to operate in, there's a node right here. Stay out of it. That's a reasonable thing in the future. But for now, this is what we can do today. And this is what we programmed into the center bar and what will be programmed over the next few weeks. So what we can do is we can click that, decide what part of the brain we're in, and what it's going to do is you're going to show up, and these things have already been made for you. So you have a left sensory motor and language, and then basically if you were to click and look at this, you get that. And then, so essentially what that means is you order the test, you click, say I want to operate in the left frontal lobe, and there you go. So what that means is that it simplifies and streamlines it, so there's just not a whole lot of reason why, even at Shady Pines Community Hospital or wherever, as long as you have a scanner that can actually do DTIs and you've activated the flag, it's always possible to get this without having experts. So let's talk about a couple disconnections, and I'll show you what I mean by disconnections. And again, remember the disconnection's a concept. You don't have to do this whole monstrous lobectomy. It's the concept of what you're actually trying to do with vis-a-vis the tracks. So medial frontal disconnection are for tumors that are sort of sitting somewhere between the motor system and the front. And it basically involves paralleling the FAT, preserving as much of the central executive network as possible, and staying out of the DMN as much as possible. So here's an example. Pretty nasty, oligo, left frontal. Again, whether or not the cognitive consequences are going to be significant is a different story. We're working on improving that. But one of the questions is very simple. How do I not do something really bad for this tumor? Now, of course, hitting ACA, and those are microsurgical questions. But from a question of where do you cut the brain, it's fairly simple. You have the motor system, you need to parallel that in the coronal plane and preserve the frontal slant tract. But you can see that what the tractography can do with tracing fibers up to the face motor cortex. So that's one cut. A lateral cut, medial cut here is with DMN. Now you can see that the AI was able to actually show the DMN is plastered up against this. So in the past, we would have thought, well, this is just a road to nowhere, but it's not. It's actually, we know from its anatomy, it's talking to this. So whether or not this is expendable is a research question, but whether or not it's pressed up against the tumor and still exists, it still exists. It may not be doing very much, but it still exists. And so that's a potential thing that you may or may decide to save depending on the context. And there's all sorts of questions you can answer, but now we at least know that it's there. And of course you have a third cut with the executive network, which is out lateral to this. So then those are your three cuts. And after that, once you've done that, everything in front of that is a lobectomy. In this case, that makes sense because it's full of tumor. But one of the things about it is, again, having a framework and knowing that this is things in the basal ganglion, basal forebrain, and maybe this isn't the best, that's a different question. And it is possible to modify this cut to be smaller, bigger, add additional things, whatever you want to come up with. It is possible in the software. To kind of show you how that works, at least to how I do this, so you can see this is a glioma. This is actually the old system. So you can see how old this video is. This is with different tractography. This is the red is the frontal slant tract. You can see the green is cingulum. And so what you're trying to basically do, fundamentally, is to make that cut safely, parallel FAT, and preserve the cingulate bundle. Okay, so again, the first thing I'm doing here is actually going in medially and trying to stay out of the DMN. And I have the patient awake, actually. That's actually that in the motor system. I want to preserve her ability to initiate so I don't make her severely abulic. And so I'm not doing a cortical mapping task. I'm actually monitoring her. And what I'm monitoring her for is, behavioral arrest. It's an initiation problem that I'm worried about. And as you see, when I put it in, what I'm trying to do now is move that cut out laterally. And the point of it is, I'm not even taking out the rest of the tumor. Once it's cut, this is easy. I mean, you can take this out with an osteotome if you want. I wouldn't recommend that, but it's, it's, from a functional standpoint, it's not a terrible idea once it's not connected to the rest of the brain. The biggest issue, though, is that the key step of the operation is this back cut. And that's where I spend most of my time doing it. Another cut, and this is a classic one, a common one, which is if you were looking at doing a temporal lobectomy, and you say, okay, I want to preserve function. Well, depends on what you're talking about. If you're talking about gliomas, that has a different mandate than epilepsy and different goals. And we need to start looking at these operations in their context. But ultimately, there are three systems. So one is, there's the medial system, which is medial to the ventricle. This is all the limbic stuff. There's a lateral system, which is the SLF complex areas. And this it would be either neglect on the right or speech on the left. And the ILF system, which is what I think Nitin was talking about, which, as you see, where it kind of sits. And most of the time, what you're attempting to do is to get past this system to get to the ventricle. Once you've done this, you're now not at risk of cutting the system. And a lot of these tumors, of course, involve the hippocampus, or they have seizures, or there's some reason to address the hippocampus. You can also decide to not do that. But once you're in the ventricle, you're past the tracks. So what the cut basically would look like if you've committed to removing the temporal lobe. Now, again, cuts are concepts, so you may not decide to do this exact operation. But if you had a glioblastoma that's filling the pole, then obviously the system is not going to be preserved in the long term if you don't attain tumor control. Connectomic doesn't tell you to never cut anything. It just says don't cut things without a good reason for doing it. And so in this particular case, you have a very extensive tumor. We'll show this case in a bit, but ultimately, the temporal lobectomy is part of a more complex insular approach. See this insular tumor as well. And it's a first destination step. Now, what are we concerned about? Well, there's two big ones. Number one, or number three, actually three if you really want to get into it. Number one, is, of course, is that the neglect system is going to define your posterior temporal disconnection. If you get too far into this, you might be able to get away with some of this. Again, the most important thing is don't cut the tract. But ultimately, this is where you should start expecting to see some potential issues if you're mapping a patient for neglect, or if you're not, where I would recommend starting to take it seriously somewhere in this area. But again, that could be reported your posterior temporal disconnection. And then that's going to give you access to get higher up in the insula, at which point you start bumping up against face motor cortex, corticospinal tract, etc. Now, usually preserving the IFOF is a good idea. In this case, you can see the IFOF is fairly attenuated. It's not very robust. And if you look at the insular parcellations, they're also mostly tumor. And this is a grade 3. So it's very reasonable to think that this tract is maybe not there. And that may not calculate into your decisions, particularly on the right side. Again, that's just something to think about. So again, you got to think about this as two cuts. One is the cut of the insula, the deep portion with the corticospinal tract. And the other is a posterior temporal disconnection, which is the means to an end. As well, there's from opercular portions. And again, it'd be best if you try to stay out of these areas as much as possible. Finally, looking at one last workhorse cut. There's other ones in the book. I don't have time to go into a book that says several hundred pages. But for example, if you were to trying to get into the medial parietal lobe, you actually want to be medial to the SLF and above the tracts. So this would be a case where, depending on your decision to be how aggressive to be with this patient, you can see that there's a big medial parietal component assist. So at the minimum, even if you didn't chase it across the callosum, which is a decision, you could at least use a medial parietal disconnection to stay safe while debulking the cyst. And so again, In this situation, your anterior cut is with the sensory motor system. You can see that this is pretty well tucked into this. This patient had significant weakness from this. It's tucked into the language system. And the DMN, as with most butterfly gliomas, is encircled. So this may be a situation where, now in this case, you also see that the posterior cingulate doesn't connect very well to the anterior cingulate. Whether or not that's a critical issue, it means that it's lost connectivity, is again a clinical question that we can't answer. But what we do know is that it's certainly, if you went in after this thing, you're going to be playing a risk with the DMN. So the cuts would basically look like this. You want to stay away from the DMN as much as you can, preserve the cingulate cortex. If you were going to come across, you need to keep in front of the cingulate gyrus between the callosum and the cingulate, and then there's your cut anteriorly with it. But now we kind of get a better understanding of why these patients have so many cognitive problems. This is not that patient. This is just another disconnection.
This video shows the medial.
Okay, hold on. Let me turn that sound off because it's blasting in my ear. Can't figure out how to do that. Okay, well, we'll skip that. I think everyone gets the point. Okay, so what we're going to do now is, so everyone let me look at the Q&A real quick. How large is the data set you validated machine learning models? We did it's trained on, I think, 500 brains, and then I've run about 450 my tumor patients through there. So I've looked at this a lot. Kusant, yeah, that's a great line, Victor. It's a classic. So what we'll do now, let me share screen here again. And let me get out of this thing, however I do that. Okay, so everyone hop on the software. And we're going to go, and I want everyone to try to follow me, so I'm going to go slow. So pick this case, tumor. And then you're going to load the wizard, and you click on Go to Viewer. And then you'll sit out for about a minute and a half while it loads this from the cloud. And I'm going to take you through the simplest steps on creating that picture that I just showed you a second ago. And ultimately, it's possible to explore all sorts of things in this case. And I encourage everyone to mess around with it and also to ask questions about how we could be doing it better. But one of the unique parts of having a cloud-based software is we can actually have everyone learn on the correct stuff. And what you want to get facile with is making targets and using this to plan, surgeries. Okay, so what it's going to do as it's loading, it's going to load the first 10,000 tracks very quickly, and then it's going to load the parcellations, and then when it's doing this, it's going to allow you to kind of break free. Now, the reason we do this is you may not particularly care about the tracks if you're going to go here and do fMRI planning for tractography, or sorry, TMS. So we didn't want everyone to be forced to sit there while the tracks upload. But if you want to do surgical planning, it's best to wait for the full tracks to get done. This file is, I think, a gig, but it clears the cache afterwards, so it doesn't really cause any issues. The amount of engineering necessary to get this to work in Chrome is a modern marvel if you really get into the amount of technical expertise it took for people to help us build this. So this is a right insular temporal glioma. It's that case I just showed. And the first thing I want everyone to basically do once we get everything loaded is to work on just making looking at some of the connections around it, working on making exports. It's fairly easy, as I showed you. And then playing around with different things and the navigation menu so that you become familiar with how to use this. So as you see now, it's brought that whole file over. Now, one of the other things that we can use as we point out is, or as we go, is that a cloud-based software has a huge advantage, which means there's no updates. You always have the updates. It's impossible that we don't actually support anything that's not up to date, and we can update it on almost a daily basis. So as Leah pointed out, there's always new things coming online, and particularly as we develop machine learning models for more sophisticated tools, which we can talk about that with anybody, obviously. So, okay, now we have control of this. So I'll kind of wait a second for everybody to get caught up, because I'm sure I got to this quicker than everyone else. Yeah, I'll give everyone a few minutes to catch up, because there's no point in missing me actually do it. I don't need practice with my own software, so. Okay, so I'm going to hope that most people have got to this point now. So when you get to this point, what you basically can do, again, it's a right-sided tumor. So obviously the first thing I would personally do is neglect. So as you can see, I've made that, and you can see there's the anatomy. Now, if I wanted to know exactly where the tumor was related to this, and again, we're working to make more compelling 2D representations that are overlays, but if I wanted to know where it was, I would go to the anatomical. This is where I have control. You can also window it if you want. But you could look at this and say, okay, where is this related to the tumor? And you can see that right in this cyst, basically the neglect system is quite close to that. Now, we can't say for sure that if you cut that parcellation that they're going to get neglect, or you undercut it. Again, clinical question, not something that our imaging is set up to answer. One day we hope to have that answer. But what we can tell you is that the best model for that system that we have to date is right there. Now, as you can see, there's an extensive temporal lobe component. There's some enhancement in engulfing some portions of the MCA. And as we work in different planes, you can kind of start to get an idea of what the relationship of this structure is to the tumor, and get an idea what to do. Now, if you're happy with this, you say, oh, that looks like a great model. I'd like to have this on my surgical guidance. You hit this export selection in the lower left. You type neglect, and it will show up here on the targets for export. You click that. There's your thing. And if you do this, right now it will send you an email in about a minute showing, and it will have a zip folder full of DICOMs that will work on your image guidance system. Okay, but let's say I'm not happy with that. I just want to get more, I want to get more things. So let's say I want to look at the DMN. So I clear that. That's going to kick me back. You should always clear what you're doing, because you don't want to have two objects merged together. And let's say I say, I don't remember, but I remember talking about the central executive network. Well, I click that. Okay. And there you go. There's the relationship of that. But I don't want it on the right side. That's actually, or the left side. I'm not going to be over there. So you can change that. Say, okay, turn off left. And there we go. And now I only have the right side in its tracks. You see that the central executive network is an SLF pathway, and they're not very big tracks, to be perfectly truthful. And there I go, I have CN. And now that's an export object. I can put as many on here as I want. What it will be is this will come back as these parcellations and these tracks as a single object in one color. And eventually we'll have it to where these colors come off automatically if you do it through the QuickBind app. where they're pre-selected so that you always get the same colors every time on the image guidance. Okay, now let's say I wanted, for example, I wanted to look at a specific parcellation. So I could go to parcellation, and I'll just pull one off that you guys probably haven't thought of, which is area 25. Well, this was the target in the DBS trials for depression. And there you go. If you wanted that for surgical planning, that's how you do it. It's fairly easy to do, as you've seen. And you can see, yep, sure enough, it's in the subcallosal cingulate. And that can be an object if I wanted to treat DBS. So DBS target. Now, we have a subcortical atlas too, and we're working on getting more detailed. So this was our first run at this. We're actually extremely impressed that the machine learning is extremely good at finding these structures with tractography. So we didn't go bulls out, but eventually this will have things like STN. That will actually take, we'll probably have that over the next couple of weeks. And so let's say I just wanted to see the nucleus accumbens. Let me pull that out in the right side. And as you can see, do I want to know, does the tumor go into the nucleus accumbens? Well, it's awful close. It certainly has some questionable areas. Let's say I wanted to look at the putamen, do that too. Yeah, it's definitely close to that. So I could just put something like, you know, and what it will do is it will fuse these guys, just FYI. So I could put basal ganglia. Now, you don't always have to do this. I'm just showing you different options. There are all sorts of ways. This, again, you also don't want to make this too crowded and cluttered, because ultimately, if you're making a surgical plan, you have to be, you know, you want to have it to where you can look over your shoulder and understand it. So I'll give everyone a few minutes to play around with it, and then we'll come back and we'll finish the course. Want to try to make sure we stay on schedule. And of course, if anyone has questions, please put it in the Q&A. Okay, so get the first question, how you use it to plan TMS. The entire next lecture is about that in the next lab exercise, so we'll get to that for sure. Can you repeat how I export it? It's very simple. Once you've selected your export here, what it does is it makes an object over here this is slated to become a DICOM. So what you would do is then you would link in test. You have to put the name. That's the only thing that's required, and the salutation. So we limit ourselves to the standard gender pronouns. And then what it's going to do is it's going to go off and it's going to make those for you in the cloud. And then it will give you an export. Right now it does it in an email, though we may fix that to do it more synchronously, depending on different circumstances, but that's how we have it done right now. So then it will do, what it will do is it will give you a zip folder with, and I'll show everyone this, because I did this yesterday, actually. At least I thought it did. It'll give you a zip folder, and inside the zip folder, you just would unzip it, and then that little folder will have all the DICOMs. So if what you're working with is something that works with the DICOM standard, it will read it and understand it and import it as an object. Not to say that every machine in the world will do it, but we've tested it with all the ones that are surgical image guidance. Do you have to upload resting state fMRI? No, not necessarily. For surgical planning, the only thing that's required to get this, and the only thing I've shown you so far, is DTI. The other thing is not the case. So if you want to do resting state right now, you have to have a DTI, because we make our atlas with the tractography. So you have to have a tractography, and it doesn't need to be extreme. It doesn't need to be these 60 directional multi-shell things. It will work with about 24 directions. Yeah, I think Rob, it has been the export has been turned off on this. Okay, so again, there'll be plenty more opportunity for everyone to discuss with us, and of course, if anyone wants to go over this with me one-on-one or whatever, I'm happy to take whatever and set up whatever. It's just in this setting, as you can imagine, with 100-something people signed up for an online course, I kind of have to we have to limit it, or we're not going to be able to manage it. Okay, so getting into the question we just asked, how do we use the software to plan and Connectomics to plan brain stimulation? And what does that even mean? Okay, so there are different ways to stimulate the brain. Most neurosurgeons know about the one on the very bottom, which is cortical stimulation and DBS. But there are non-invasive ways too, and DBS is really good at stimulating basal ganglia. Probably you can put it in a cortical area in some cases, but again, some of these things may not be necessary or even prudent in certain circumstances. So of course, we're not putting DBS electrodes into post-op patients. It just doesn't make sense. And so there's a lot of other options that are FDA approved, in many cases have extensive data. And the one that I'll focus on is TMS, because it fits very neatly with the kind of way we think about the world. And more importantly, it's safe and effective in many patients. So this is how different ways to deliver it. So of course, DBS, we all know, you put an electrode in the brain, you hook it up to a battery. How TMS works is that there are two coils, or one coil, and as electricity goes around in a circle, it sends a perpendicular magnetic pulse into the brain. And so this is kind of what the field looks like. It's not perfectly focal, but we know that the vast majority of the activity happens in a space about that big, depending on the coil. There are other non-focal stimulations, like what's called transcranial direct current, where you basically just hook up somebody to almost like hooking up to a very sophisticated battery. And they, believe it or not, it actually does a lot of good in certain circumstances, but you see that you're not very precise with it, and they work differently. So one of the things that surprised me when actually angered me when I first came across this, was how much data there is on TMS. So these are all the diseases that people have done at least more than one randomized trial on. And you see that it spans the spectrum. In fact, it's pretty much everything except neurosurgical patients. And part of this was that people were very worried about seizures, because in the initial protocols, people got seizures even if they didn't have seizures prior. And so as a result, there was a lot of concern about epilepsy and seizures, and craniotomy patients were just put on the list and no one ever questioned it. We have not seen this problem in our own practice. More importantly, what we notice is that in many cases, it can make either moderate or substantial improvements. And for example, one of the reasons it is not FDA approved for stroke right now is not that it doesn't have positive studies. It's that if you don't look at things like the corticospinal tract, or you test people or treat people a year after their stroke when they finally ramble into a research study, you're going to get less good results than if you do it earlier and you look at whether it's even possible to rehab someone. And part of this is the stroke studies have trouble getting access to the kind of imaging that we're providing here and answering that question in a timely fashion. You know, you have to go spend 2 weeks doing offline processing to figure out whether you can put someone in a TMS trial. It's probably not going to happen very often. It's just going to be too difficult. But notice that it is FDA approved for depression and has been. There's multiple companies selling that device for that indication, and not a lot of controversy. Does it work for that disease? It also just recently got FDA approved for OCD. Interestingly, the target for OCD is the SMA. So basically, that's a fascinating finding, and it's been repeated in 2 trials. So it shows you that the SMA is not as much of a motor area as it is a cognitive area that happens to be part of motor. Again, this is the coil we use. The nice thing about a butterfly coil is it has two different wires going in opposite directions, so the field is concentrated between the two coils. It's not focal. It also doesn't go deep into the brain, but it's reasonably focal, as about as focal as you're going to get with a magnet. And there are different ways you can deliver this. So the traditional way is some variation on this, which is what's called 10 hertz. It's basically 10 times a second. And it takes about half an hour to do that. But recently people have come up and studies show that these are equivalent in efficacy, what's called theta burst. So what you do is you give 3 pulses of 50 runs, 50 pulses in clusters of 3. That's where the word theta comes from. And the burst is the 50. Now, if you give this in an intermittent fashion, meaning you go for a while in a train and then take a break, it actually probably turns the cortex up in most people in most situations. And if you do continuous, it wears out the cortex. And the effect from this lasts for about 45 minutes, where the cortex is either hyper or hypoactive. Now, this isn't perfect, but it's pretty good. And most of the studies show that most of the time this concept holds. But the beauty of theta burst is that it's actually a lower current, so it's 80% of motor threshold, whereas this is about 120% generally. And the treatment, instead of 30 minutes, is 5 minutes. So this lets you treat multiple targets. It also lets you treat multiple times a day. And there is recently trials showing that you can do this up to 5 times a day, and even one person 12 times a day. And the results are basically the same as if you spread it out over a month. And so that, for us as neurosurgeons, is a massive deal, because it means you can treat someone for 5 days and send them into rehab or chemotherapy or whatever. And this makes this possible. How does it work? Well, nobody knows. In fact, if you go to the Brain Stimulation Conference, which it will be next February, it's every 2 years, there's an entire day dedicated to the mechanism. But the best explanation of this is that the waveforms that are delivered by TMS that are in the efficacious range reduce the GABA tone of the cortex and make the area prone to plasticity. Now, what that means, importantly, is that it's important to combine this with therapy. You don't really get the real benefit. And so what we do is we structure our clinic where the patients get that therapy between sessions. So we zap them for 10 minutes and they therapy for 50 minutes. So it's an intense week. But what it means is that you're really utilizing this technology in the way it was designed to maximize outcomes. And whether or not it's the aggressive therapy or the TMS or both, we don't really care. The patients get better in ways that we haven't really seen very often in our standard approach. The risk of this is very low, and I keep saying that, but it's pretty much a general belief and universal result in the findings. So a couple things. The risk of a seizure has been measured with theta bursts at about 8 in 100,000. So my thought is, we're neurosurgeons, seizures are on our boards, we can handle it. I've never had to deal with this. There can be a little bit of uncomfort, particularly if you're over the temporalis muscle. Most of the time the patients adapt to this, but that's one thing to note if you're picking a temporal target. And if you have to, you can switch from theta burst to a longer protocol. The theta burst is a little more intense than this because of how fast it's firing. It's firing about 150 times a second. Most of the time, the only symptom we see is people get tired. Part of this is we're aggressively rehabbing them. The bottom line is very low risk, and there's never been a study, to my knowledge at least, that shows that the placebo group did better. So we don't think we're making anybody worse with this. So either they get no benefit because we're not in the right place, or it's the wrong patient, or whatever, or it helps, and sometimes dramatically so. So interventional neurorehabilitation is utilizing image guidance, and Connectomics to try to take a proactive stance towards rehabbing people after injuries, and thinking about this like neurosurgeons think about this. And this is a really good example of one of the reasons this hasn't translated, in my opinion, is when it evolved in psychiatry, they don't order a lot of scans. They're not scan ordering people, where they don't use image guidance, And so it took a very long time for them to come to the conclusion that we came to a long time ago, which is, if you don't use image guidance, which is what this study is showing, even experts are hitting different parts of the brain. And I took this and mapped this onto our thing. What this is showing is that in some cases they're hitting this, and in some cases they're hitting this. And this is non-trivial because they have different connectivity. Furthermore, area 46 is part of the salience network. See that? That's middle cingulate, anterior insula. Whereas 8C is the executive, anterior pole, 8C, this area. And so you're not even hitting the same network. And this is actually a very small distance in the Euclidean space. Because remember, this is an unfolded brain. So when you fold it, the areas are closer together. So it's important to know what you're trying to do and to make sure that you're actually in that area. And this is something that, of course, is intuitive to neurosurgeons. It's just coming into the psychiatric world where people are starting to say, for sure, we need to start doing this. And one of the thoughts is, and Kostas brought this up a little while ago, if there's a hole in the brain, TMS is probably not going to cause tracks to go across the hole of that. What we're probably doing is we're upweighting certain connections to get around the deficit, to get other areas to take over, to supplement what's left. There's a lot of potential ideas that you could have. And this is what the treatment looks like. So again, this is one of our former fellows. This is the patient. You can see she's fairly impaired. And you can see that this is the target. It's selected. It's exported from the software. It's put on image guidance. And painless, fast, and that was an intermittent run. If you notice that it stopped, so it went for a little while and stopped. That's an ITVS run. Every time you hear a click, I think it's roughly 150 pulses. So again, we use theta burst, 5 to 8 minutes. We usually treat multiple targets. We do an accelerated protocol. We wait between treatments for an hour, and we give aggressive therapy aimed at the patient. Here's some of our preliminary results. This is updated from a paper that's currently being reviewed. We've done some cases since. The biggest thing about it is this. We've seen a lot of people improve, and including some very chronic people that we did not expect to improve. And the bigger issue is that we have had no one have a problem with this. So what this means is that this is kind of open season for us, I think, to really start to take this seriously as something that we should explore, because we don't have a lot to lose in this. So how do we plan this? Well, the first question out of my mouth, and anybody, whether they're coming in for mental illness, whether they're coming in for whatever, is what do you want to make better? Sometimes it's obvious, right? If they're paralyzed in the leg, that's, to get too deep into that. But oftentimes it can be hard to say. But the most important thing is you need to know where to look, because you can't look at the whole entire matrix. That's just not realistic. It's not even desirable. You need to drill down on what it is. And part of our goal as a company with machine learning is to subset the data where you can see that automatically. You want to look at the structural images. You got to know what the hardware looks like that you're working with. You obviously don't want to, if someone's missing a parcellation, to pick that. You don't want to. You want to have an idea of how they got to this point. What's the mechanism? And then you look at the montage, you pick the target, which ultimately are columns, and I'll show you how to do that. And you select what you're going to do and how you're going to do therapy between them. Again, having smart physical therapists, speech therapists, people who are committed to this program is essential for success, unless you want to do the PT yourself. My system has worked out to where I basically am the target picker and my team does everything else. So that's good. That's kind of where you want to get to as a neurosurgeon to incorporate this into your practice. So again, you want to look at what's there and what's missing. One of the things that we can do as a software to help is actually our machine learning will tell you what's missing. It actually, we're also building an algorithm that'll tell you, well, it's there, but it's not really normal. That's actually a complicated concept, but what we would say is, well, this is an unhealthy parcellation. It's not really connected for very much. There's 3 voxels and it's supposed to be 500. But right now we can tell you ones that don't exist. And the next step is to think about the disease. Ultimately, Connectomics is not going to answer the question. It's designed to augment your intelligence. That's why it's IA. And so you have to think about, how do you think this is happening? For Alzheimer's, this is a diffuse loss of problems. Whereas obviously with tumors, we kind of understand that, the focality of it. Whereas other situations, this is a rhythm issue. And thinking through that is a good way to start to interpret what you're seeing. And then you got to pick a montage. And eventually we hope to have montages for you. But in the short term, you have to kind of aim to where you think the problem is. And a montage, as you remember, is a collection of comparisons between every parcellation and every other parcellation on certain networks or areas of interest. So for example, in this situation, you have CEN or DMN, CEN, they're mostly red. In the cross diagonals, they're blue because these networks are not supposed to talk to each other. They're opposite, so they don't correlate, for example. And what you would do in the situation is you might find that this is not supposed to be there. And then you can export that to a file in our software and pick it as a target. So again, how do you do that? Well, the first is pick a column with a lot of problems in the area that you're interested in. Everyone is going to have anomalies, everybody. It's just statistics. It can be false positives. But if something has 10 anomalies and it's in an area that's linked to the problem, the chance that that's statistical noise is a lot less. Also, we want to utilize prior knowledge, right? So if someone has a motor problem, look at the motor system. And if you can't pick an obvious one, pick the motor cortex. It's better than nothing. But a lot of times we find other targets. And in general, we kind of aim for 2. That's 2 to 3 is about most of the time. I found that tends to work better. Again, this down on the left can be interesting if you're knowledgeable, but this one on the right is a lot easier to understand. And we're constantly working on making our anomaly detection tools better. But this is what we have now, and I think it's pretty good. And it's taught me some things about how to treat these patients. So again, white is normal, blue is less correlated than normal, red is more correlated than normal people. This is trained on a training set of normals. And black are areas that we don't show you because they're very variable, they're noisy. And once you pick that, you decide, do you want it up or down? If it's up, you want it ITBS. If it's down, you want it CTBS. It's a good idea. It may be that the opposite pathway is true in some circumstances. Again, a clinical machine learning question, not something you can answer on this. And then, of course, picking a treatment that works for the patient. And again, this can be anything from cognitive rehab, it can be speech therapy. You have to get it patient by patient, and having a team that wants to do this. What I found is that most therapists they see one of these patients and they're sending even people who aren't appropriate to you because they're amazed at what this can do in some of these people that they've in many cases treated for a long time without a lot of success. So running through a couple examples, and the possibilities are literally as big as you can make the world look. But these are ones that are low-hanging fruit. We understand it. I can tell you what to do. I've treated patients and seen good results in some cases. And so again, the first and most important part is, what's the structural architecture? If the corticospinal tract's gone, the corticospinal tract's badly injured, if you see tons of flare up and down where that is located, then that may not be, you could try it, but you have to be honest with the patient that that's less likely to work. Having said that, I find that machine learning tells me things that I don't know all the time. And so the anatomy of this, okay? So this spits out primary, ventral premotor, dorsal premotor, and SMA, but it also, an area that you guys probably haven't thought of, which is the cingulate motor. Now that's hard to hit with TMS, but it's an important part of motor planning. And so it's not something that I had ever heard of until I got into Connectomics. This shows you that the motor system is far more complex than DTI can show you. And this is the value of CSD. So not only can you see all the fibers going to the area, you can also see connections to the basal ganglia, thalamus, inter-brainstem connections. I mean, it's pretty impressive how this can perform. And it's also important to note that there's crossing. So the frontal S slant track is connecting the SMA to the ventral premotor area, okay? And Broca's area, I mean, they kind of are the same thing ultimately. But it also connects, there's cross connections. And so if you're going to interfere with the SMA, you also want to at the very least make sure that the other side can take over and compensate for it. And that's really easy to see in the software. You can see we've kind of subset it in this manner. And so, but what's really impressive of this is there's a big hole in the brain, and this thing is able to map the parcellations and connections right next to it. And so you can see that this is what machine learning can do that we just can't do ourselves. So this is a couple cases. This is a case that I've shown to a lot of people. It's pretty cut and dry. This patient woke up paralyzed after an aggressive surgery. I didn't do the surgery, but I did help rehab him. And you can see that there's not a structural reason for this. The cortical areas are in place. The corticospinal tract's intact. And so this is a functional disturbance. And the functional disturbance is both that there's hypoactivity on the ipsilateral side and hyperactivity in the basal ganglia on the left. So we picked ITBS to stimulate the bad side, CTBS to turn down the good side. And in about a week, this is what we went from. So what she's basically explaining him to do is pretend like imagine you're moving your leg, because he can't move. He has a little bit of hip abduction. And 3 days later, he's like this. Now, he probably isn't headed towards the Olympics this year, but he is back to surfing now. And he continued to improve after this. This is just the video where I have video. So it is possible that he would have made some improvement without our treatment. Don't know, can't randomize him, but 3 days is pretty fast. And the thought process is, even if he was going to get better over 5 months or something like this, if you speed that up to, a week, that means he's into radiation quicker, he's less likely to DVT. We all know the issues regarding, leaving somebody hemiplegic after a surgery. Now, it's important to note that that isn't the only pattern we see. We see all sorts of ones. So this is somebody who woke up totally plegic after a first surgery, got a little bit better, has some arm weakness. After a second surgery for this cingulate tumor, woke up plegic again. Now, plegic, like 0 out of 5. And so first thing we looked at is the corticospinal tract intact, and it looks pretty good to my eye. We thought maybe it's the leg motor cortex, but actually his leg began to recover, and he actually was real problem when by the time he made it to the treatment was actually his arm. So, but at least you see that there isn't a complete severing of the tract. He might have nailed a few fibers here or there, but so by the time we were treating him, it's about 3 weeks after operation. The swelling should have come down by then. And it wasn't immediately clear why he was so weak, why he did so bad, until we noticed that he didn't have cingulate motor areas. See that there's missing parts of that area. We looked at his cross tract, it looks okay. And then when we looked at the connectivity, you see that there's a few areas. For example, there's columns of the motor system that are blue. This is supposed to be one of the most bright red parts of the brain. As well, there's parts where the basal ganglia don't talk to the motor system at all. And so basically, we picked these two targets here, one in the left SMA and one in the right PMA. And you can imagine we did kind of, in this case, we turned both of them up. We're trying to get him to drive off of one side to help the other side. And so we turned it both up, and he actually improved to better than pre-op. He still has some hand weakness, but he's a lot better. Again, modern language system to run you through what it has in there. 55B, 8C, that's 44 and 45. There's the SMA portulations. These are parts of the Geschwin area that are also part of the executive network. And then these are STSDP, which is the part of Wernicke's area, and this is some other parts of the naming structures. Again, there's a lot of different ways you can look at the language system, and it's also important to make sure you know whether you're treating a speech problem where you really need to be looking at motor areas versus a phonemic problem where you need to be looking at things like 55B. I think that is an absolutely great target. I've treated a lot of people at that target with good success since I discovered it, or discovered what it was doing. And I just tried it on someone one time and it worked great. So I've been using that ever since. It's kind of one of my go-tos. It's almost always abnormal in people who have language problems in some way. But then, of course, you can get into much more complicated situations where you're looking at something like reading. And that's actually what we're going to cover in this, which is looking at language versus vision. You can come up with all sorts of potential combinations out of this. So this is a case that we're going to go through. This is someone who's had multiple surgeries, not by me, for low-grade glioma. Speech just seems, you have a conversation that you wouldn't notice anything particularly wrong, just a little bit of word finding delays, but nothing that you wouldn't expect for someone who had been through what she'd been through, but she almost is alexic. If you talk to her, she's very, very minimal. And it's not immediately obvious why this surgery would do that, other than maybe just verbal memory problems in general. When we looked at this, the language parcellations are all there. You know, the only thing she's missing is her accessory language. But why wouldn't she have anomia, which she really didn't have very mild anomia or dysnomia, but she has a profound alexia. So how do we do this? Well, we start looking at how the language system talks to different areas. And when you look at language and vision, you know, you don't have to be an expert in this area to notice there is a ton of anomalies between how these work. You can pick whatever you like. As you can see, 55B has an entire column to its own. And so, again, in the interest of time, we could go on and on about different possibilities about how to treat executive dysfunction. This is a really fascinating case that I'll end on. This is a guy who had a severe pneumonia, physically recovered, never cognitively recovered. He had a workup, saw 20 doctors. He's an executive. He couldn't work. And he was originally sent to us for anxiety, but in reality, he was just anxious that he couldn't do his job because he couldn't multitask. So even though all of his tests have been negative, that is his CEN. It literally looks like a bomb went off and everything is down. And we picked those 3 targets and changed his life with them. He's a true believer in this software. And so that for us was really amazing that we could take somebody who had such a vague, we've all met this patient, nobody knows what's wrong with them. And now we actually have something that can at least start to get towards the bottom of this, as opposed to just putting our hands up. So in the interest of time, hopefully we can get everyone on here, but I'll try to hustle through this because I've done too much talking. Okay, so, it's conference. Stefan and his English. So if you go to case 3 and just go straight to the viewer, and what we're going to actually look at is the Connectomic. So this has a DTI and fMRI loaded. And we're going to let this load for a second, but we don't have to wait until everything is loaded. Okay, so once it gets to the, past the parcellation stage. Now again, if we were going to go through this whole exercise, you would want to look at all the tracks and all the anatomy, but I've already shown that to you. And I want everyone to at least get the opportunity to look at the fMRI targeting tool that we have. Okay, so now it's going to go on and try to pull up the rest of the tracks. Once it delivers this is the matrix. And again, the tool is exactly the same. Okay, so let's say I want to look at this patient's language. Okay, now this is the anomaly detector. You may not want that. So if you want to see the raw data, you go over to Connectomic on the right and you just switch. This is the raw view. So you can see, language system talks to the language system. It looks a little bit more correlated than normal. But when I come on to the anomaly, this is going to tell me what's abnormal. So as you can see, as we load this, you see that there's areas that are hypercorrelated. Now, this may be compensatory. It may be pathologic that these 2 areas, 44 and 55B are overcorrelated. It's hard to say, but it's certainly not normal. Now, as you see, when we come over the black, it's nothing there. But if you look at it, there's an X and a Y. And as I hover over, it gives me X, Y, and the number. The X is the column, Y is the row. And when I pick this, so let's say I say, 55B looks bad. Let me click this. What I did, it's going to go over to this thing once it finishes loading all this. And we'll give this a second while it does its thinking. Okay, so what it did is it took that column that I clicked on. Let me show you that again. 55B, and it pulled up 55B off the atlas. And then what you can do is you say 55B, and I want to turn that down, so I'm going to do CTBS, done. There's your target. And that will show up over here in the export, just like everything else. Now, that may not be what I want to do, because this is a fairly simple map. So in this case, maybe I want to do vision. So now I got a bunch of other anomalies. Now, what you see here is that anything I click over here, it will add that to the matrix and then compare it against whatever else is in the matrix. So what you can see is the blue dots say that these areas are language, and the orange dots say that these are vision. If we wanted to, we could look at the DMN in there. You can add whatever you want. It's even possible to add tracks for people who are really interested in this. And let me just clear this for a second. So if I wanted to, for example, just say how much of the parcellations connected with IFOF, how much are they working, right? So I could click IFOF, and what it will do is it will go in and say everything in our map that linked to IFOF, this is how it's doing. Okay. As you can see, there's a lot of down in this, probably because parts of the IFOF have been damaged from over the years. That's a hypothesis. It may be some other kind of unrelated thing. But you also notice that there's some areas that are very strongly overcorrelated. So these are the color does matter a little bit. Eventually, you develop an eye for that. If I was treating a mental illness, I would click these guys, CN, DMN. And actually, let me clear that so it's easier to read. So now I wouldn't do this for no reason. So I wouldn't just look at this per se, unless she came to me with this, specific problem, either cognitive or emotional or things related to the higher functions. But you can see that she's got a lot of stuff. And again, not entirely surprising given the temporal lobe is out and she's got other issues. She's had a lot more issues going on than you would expect. And I wouldn't recommend looking at that for no reason. But if you were to look at this, for example, 8AV right here, actually wrong one, in an anxiety patient, I have never seen one have a normal column. It's almost always full of stuff. And it's almost always up and it's always on the left, which again, as I pointed out, that's one of the asymmetric parcellations. So the goal of this is, again, how we design this is any potential combination that you could come up with, you can subset it and pick it. And this can get more deep. So eventually what our goal is that we have these for different diseases, so schizophrenia, autism, and that would be built into the QuickMind window. So if you say, I want to look at depression, well, what do you want to do in depression? Do you want to make their cognition better? Do you want to improve psychomotor retardation? And that you have a subset of parcellations that were relevant to that, so that you're actually looking at the subset that you're supposed to look at. There are also other tools that we're creating in the background. But in this particular patient, how I treated them, to kind of close circle here, I looked at language, I looked at vision. As I zoomed in, there's a bunch of problems. Let's see, that seems to be a guy worth dealing with. And I remember for sure I treated 55B, and I may have treated this one. I forget exactly what the third one was. But you see that these are columns where this parcellation talks to that one normally, that one. And essentially we did this in combination with reading therapy, and her scores improved from about 8% of max for her level of education to 75%. So she didn't become normal, but that's a quantum leap for basically not putting her through a whole lot of rigmarole. And the hope is that then that can jumpstart it where now she just continues to read and continues to make progress. And by the way, she was a year out from her most recent surgery, which left her alexic. So it really shows that we don't understand where the plasticity window really begins and ends. So that's what I have. And I'll take questions. So one question from the previous one. Interestingly, I have a large right temporal GBM to do tomorrow. Patient has hemianopsia, weakness. I did DTI map and has optic radiations of the medial aspect of the tumor. My approach will be transsulcal. Is this safer to preserve the neglect pathway? The answer to it is sulci are often the shortest path, but shortest paths may not be better paths. What we haven't tracked is to my knowledge, I don't have a clear thing to tell you that the superior temporal sulcus is doing, or the middle temporal gyrus is doing on the right side. That's important. If you're anterior to, say, Heschel's gyrus, then you're probably not going to be in the neglect system in most people. So you'd probably be fine. But again, I can't tell you for sure that there wouldn't have other consequences, but I think it's probably okay. Have you used it to treat autism spectrum disorders? The answer is we've treated one and we're about to treat another one. We have a model for that actually. The machine learning what we did is we tried to recognize the connectomes of autistic patients. It performed about 85% accuracy. And the person that we treated had the inability to look people in the eye for their whole life, basically, and a lot of anxiety around that. And we treated them with that. And basically the therapy for that was social conditioning, where we pulled some ideas out of the autism literature. And the results for that were dramatic. So that's an N of 1. And again, you're not going to make all of autism better. Okay, that's not realistic. It's a pan brain disease. You have to get this down to a transdiagnostic where it doesn't matter what the diagnosis is. It matters what the connectivity problem is and what are you trying to improve, because that's realistic with this. You can realistically improve a symptom to some extent in some people. But in this particular patient that we treated, the model knocked it out of the park. It did great. But whether that's going to scale, I don't know. Okay, so if there are no more questions, we're at time, but please feel free absolutely to contact me, to contact us. As you can probably tell, if you're talking for 3 hours straight to myself, I can probably talk your ear off on this. And again, we'll be sending out a survey. And the biggest thought that we have in this situation, we want to make it better. And we want to engage with people on how do we make it better? How do we make tools that are actually useful, that people understand? So the answer to it is, again, Leo and the organizer of the course can help get you in touch with me, but I'll actually quickly share a slide here. And it has my email address on it. So if anyone wants to talk to me more about it, I'm pretty flexible. There I am, looking like a surgeon. That email address, you can email anytime you want, and I will, if you want, we can dive as deep as you want. And the question about the pontine cavernoma, they've been given rehabilitation, improvement TMS to the cerebellum. Cerebellum TMS is extremely underrated. We've seen some really amazing results from a collaborator out of Shenzhen where people have walked out of wheelchairs. I wouldn't say that that's a standard with that, but it is really underrated and very easy to do. If basically, as far as getting upload the data, this is something to talk about. We can work on getting the software to you. And at which point there's a million questions. I mean, I think everyone we've ever shown this to who's intellectually curious person has said that there's a million things that they can come up with to study, because this is a massive quantum leap over what we have right now, in my opinion, obviously. Obviously, I'm biased. I spent 8 years of my life and years of my life helping build the software. But I think I think it really is a big step forward for us. Next session. If someone wants to set up a session, I can teach this course every day if you want. Well, not every day, but if someone wants to organize a course, as you see, it's quite easy to do this on the internet. And as you see, we can also scale this course and get the word out to as many people as possible. Okay, I think, so everyone please fill out your surveys, and if there are no more questions, I'll hang around for a little while. And hopefully everyone gained some new insights and ideas from the course. So thanks everyone for coming. And of course, if anybody, I want everyone to also say, if anybody wants to help us work on the next generation, give us feedback, we're absolutely 100% committed to making the software as good as possible and to get as many people to really get to using it. We didn't make this so that we could have it sitting on our shelf. So we really want people to, we really want this to be an ongoing an exercise. if you have the relevant ones, yeah, if you send me the images, I can show you what it looks like, and we could discuss cases. Yeah.
Mike, thank you for your time today. I think if we close this webinar, the survey should automatically pop up for anyone who's currently on the line. And if not, we'll just email that survey to you as well. As we've mentioned, any feedback you provide is extremely valuable for all of us, I think. And we do appreciate your time.
Yep, absolutely, guys. Thanks everyone for coming and listening to me talk for 3 hours. So thanks everyone.
Thank you. It was great. Appreciate it.